In 2022, a telescope a million miles from Earth began sending back images of the most distant objects ever observed. The images showed galaxies as they appeared when the universe was very young, a few 100 million years after the Big Bang in the first chapter of cosmic history. Astronomers had spent decades predicting what those early galaxies would look like. They expected to find small, faint, scattered clumps of newborn stars. Faint smudges, just barely coming together. That is not what they found. They found galaxies that were too big, too bright, too fully formed for their age, galaxies that, according to the standard model of cosmology, should not have had time to exist yet. Some astronomers said, quietly at first and then more openly, that the new telescope might have broken cosmology. Tonight we'll move slowly through the whole story. What the James Webb Space Telescope actually saw, why it was so unexpected, whether it really broke our understanding of the universe, or whether it simply revealed how much we still have to learn. If this kind of slow, careful exploration is what you came for, consider hitting like and subscribing. It helps more than you might think. Now, let's begin. The James Webb Space Telescope is the largest and most powerful telescope ever placed in space. It was launched on December 25, 2021, after more than 2 decades of design, construction, and repeated delays. It cost approximately $10 billion. It involved thousands of engineers and scientists across multiple countries and space agencies. By any measure, it was one of the most ambitious scientific instruments ever built, and its primary purpose was to look further back in time than any telescope before it. The telescope is named after James E. Webb, who led NASA during much of the 1960s through the era of the Apollo program. The instrument itself is a marvel of engineering. Its main mirror is 6.5 meters across, far larger than the mirror of the Hubble Space Telescope, which it was designed to succeed. The mirror is made of 18 separate hexagonal segments, coated in a thin layer of gold to optimize their reflection of infrared light. The segments fold together for launch and unfold once the telescope reaches its destination, forming a single large mirror surface. The destination is not low Earth orbit, where Hubble circles the planet. The James Webb Space Telescope is located approximately 1.5 million kilometers from Earth, at a position called the second Lagrange point, or L2. This is a special location in the gravitational geometry of the Earth-Sun system, where a spacecraft can maintain a stable position relative to both bodies while orbiting the Sun in step with the Earth. From L2, the telescope can keep its back to the Sun, the Earth, and the Moon all at once, shielding its sensitive instruments from their light and heat. The shielding is essential because the telescope is designed to detect infrared light, and infrared light is, in essence, heat. Any warmth from the Sun or the Earth, or the telescope's own electronics, would overwhelm the faint infrared signals from distant galaxies. To prevent this, the telescope carries an enormous sun shield, about the size of a tennis court, made of 5 layers of a specialized material that reflects and dissipates heat. The sun shield keeps the telescope's instruments at a temperature of around 40 Kelvin, which is approximately minus 230 degrees Celsius. At that temperature, the instruments produce little enough heat of their own to detect the faint infrared glow of the early universe. Why infrared? The answer lies at the heart of why the telescope was built. Light from the most distant galaxies, having traveled across an expanding universe for billions of years, arrives at the Earth stretched to longer wavelengths than it had when it was emitted. Light that left a distant galaxy as visible or ultraviolet light arrives, after its long journey, shifted into the infrared. To see the most distant, and therefore the earliest, galaxies, a telescope must be able to detect infrared light. Hubble could do this to a limited extent. The James Webb Space Telescope was designed to do it far better, with far greater sensitivity, reaching far further back toward the beginning. The telescope carries 4 main scientific instruments. They include cameras that capture images at infrared wavelengths and spectrographs that split the incoming light into its component wavelengths, allowing astronomers to analyze the composition, distance, and motion of the objects being observed. The combination of imaging and spectroscopy is what makes the telescope so powerful. The cameras can identify candidate distant galaxies. The spectrographs can confirm their distances and reveal their properties. The instruments were the product of careful design choices, each made to maximize the telescope's ability to study the early universe. The wavelength range, the sensitivity, the resolution, all were optimized for the goal of seeing as far back in cosmic time as possible. The telescope was, in a real sense, a time machine, built to capture light that had been traveling toward us since the universe was young. After launch, the telescope underwent a months-long process of unfolding, cooling, and calibration. The mirror segments were precisely aligned. The instruments were brought to their operating temperatures. The whole system was tested and tuned. By the middle of 2022, the telescope was ready to begin its scientific observations. The first images were released in July of that year to widespread public attention. They were stunning, sharper, deeper, and more detailed than anything that had come before. But the most significant images were not the ones that drew the most public attention. The most significant images were the deep field observations, long exposures of small patches of sky, capturing the faint light of the most distant galaxies. It was in those images that the surprises began to appear. The telescope had been built to see the beginning. What it saw when it looked was not quite what anyone had expected. To understand why the James Webb Space Telescope can see into the past, it helps to think carefully about what it means to see anything at all. When you look at an object, you are not seeing the object as it is in the present moment. You are seeing the light that has left the object and travelled to your eyes. For everyday objects, this distinction does not matter, because light travels so fast that the delay is imperceptible. The light from a lamp across the room reaches your eyes in a few billionths of a second. The light from the sun takes about 8 minutes. You see the sun not as it is now, but as it was 8 minutes ago. For astronomical objects, the delays become enormous. The nearest stars are several light years away, which means the light you see from them left years ago. The centre of our galaxy is about 25,000 light years away. We see it as it was 25,000 years ago. The Andromeda Galaxy is 2.5 million light years away. Its light has been travelling for 2.5 million years. As you look at more distant objects, you are looking further and further into the past. This is the fundamental principle that makes telescopes into time machines. To see an object that is 1 billion light years away is to see it as it was 1 billion years ago, because that is when the light you are now receiving left the object. The most distant galaxies are billions of light years away, and the light from them shows us those galaxies as they were billions of years ago, when the universe was young. There is no way to see them as they are now. The information about their current state, if they still exist, will not reach us for billions of years. The James Webb Space Telescope exploits this principle to study the early universe. By observing the most distant galaxies, it observes the universe at its earliest epochs. The light from these galaxies has been travelling for almost the entire age of the universe. When it left, the universe was only a few 100 million years old, a small fraction of its current age of nearly 14 billion years. The telescope sees these galaxies as they were then, in the universe's infancy. But there is a complication, and it is the reason the telescope is built to detect infrared light specifically. The universe is expanding. As light travels through expanding space, its wavelength is stretched along with the space it travels through. Light that was emitted at a short wavelength arrives at a longer wavelength. The longer the light has been travelling, and the more the universe has expanded during that time, the more the wavelength is stretched. For the most distant galaxies, the stretching is dramatic. Light that left these galaxies as visible or ultraviolet radiation has been stretched over billions of years of travel through expanding space, all the way into the infrared part of the spectrum. By the time it reaches us, it is no longer visible to the human eye. It can only be detected by instruments sensitive to infrared wavelengths. This is why the James Webb Space Telescope was designed around infrared detection. To see the most distant, and therefore the earliest, the objects, it had to be able to see the stretched, reddened light that those objects produce by the time it reaches us. The amount of stretching is quantified by a number called the redshift. A redshift of 0 means no stretching. The object is essentially at rest relative to us, and its light arrives at the same wavelength it left. Higher redshifts mean more stretching, which corresponds to greater distances and earlier times. The most distant galaxies observed by the James Webb Space Telescope have redshifts above 14, which corresponds to a time only about 300 million years after the Big Bang. The light from those galaxies has been stretched by a factor of about 15. Light that left as ultraviolet radiation arrives as infrared, with a wavelength 15 times longer. The combination of these principles, that distant objects are seen as they were in the past, and that their light is stretched into the infrared by cosmic expansion, is what makes the James Webb Space Telescope a tool for studying the beginning of the universe. It looks at the faint infrared light from the most distant galaxies, and in doing so it looks back in time to the earliest epochs of cosmic history. It is, quite literally, a machine for seeing the past. There is something almost vertiginous about this. The telescope is not modelling the early universe or simulating it or inferring it indirectly. It is seeing it. The actual light emitted by actual galaxies in the actual early universe is falling on the telescope's mirror right now after a journey of more than 13 billion years. The past is not gone, it is still arriving, in the form of ancient light, carrying its information across the vast gulf of cosmic time. Consider for a moment the journey of a single particle of light from one of these distant galaxies. The light was emitted when the universe was perhaps 300 million years old. At that time there was no Earth, there was no Sun, there was no solar system. The matter that would eventually form our planet was scattered across the cosmos, not yet collected into the cloud that would collapse to form the Sun and its planets. The light began its journey in a universe utterly unlike the one we inhabit. The Earth formed about 4.5 billion years ago. The light from these distant galaxies had already been travelling for more than 9 billion years by the time the Earth came into existence. It continued travelling as the Earth cooled, as the oceans formed, as the first life appeared, as that life evolved through billions of years into the complex biosphere we know today. The light travelled on through all of this, indifferent to the events unfolding on the small planet toward which it happened to be heading. The light continued travelling as the dinosaurs rose and fell, as mammals diversified, as the first members of the human lineage emerged in Africa. It travelled on through the entire span of human evolution, through the development of language and tools and agriculture and civilization. It travelled on through all of the recorded human history, through every event that any human being has ever experienced or recorded. And it arrived at the James Webb Space Telescope's mirror in the year 2022, having completed a journey of more than 13 billion years. This is not a metaphor or an exaggeration. It is a literal description of what happens when the telescope observes a distant galaxy. The light that it detects is genuinely that old. It genuinely left its source before the Earth existed. It genuinely travelled across the entire subsequent history of the universe to reach us. The telescope is detecting a signal that has been in transit for almost the entire age of the cosmos. The implications of this are worth sitting with. When astronomers look at these distant galaxies, they are seeing the universe as it was before almost everything that we think of as history. The galaxies in the images are not contemporary objects. They are ancient, so ancient that the concept of ancient barely applies. They existed at a time when the universe itself was young, when the structures we see around us today had not yet formed, when the conditions of the cosmos were fundamentally different from what they are now, and yet the light is here, now, falling on the telescope's mirror. The past is not inaccessible. It is, in a strange way, still present, carried in the light that continues to arrive from the depths of cosmic time. The telescope is a kind of window, not into a distant place exactly, but into a distant time. Looking through it is looking backward, across billions of years, to the universe's earliest chapters. There is a limit to how far back this looking can reach. The universe was not transparent in its earliest moments. For about the first 380,000 years after the Big Bang, the universe was filled with a hot, dense plasma of charged particles, and light could not travel freely through it. Light was constantly scattered by the charged particles, the way light is scattered inside a fog. Only when the universe cooled enough for the charged particles to combine into neutral atoms did it become transparent, allowing light to travel freely. The light from that moment of transition is still detectable today, as the cosmic microwave background, the oldest light in the universe, dating from when the cosmos was just a few 100,000 years old. The galaxies that the James Webb Space Telescope observes are younger than the cosmic microwave background, but still extraordinarily old. They formed in the period after the universe became transparent, but while it was still very young, the first few 100 million years of cosmic history. This is the era that the telescope was designed to study. It is the era when the first galaxies formed, when the universe transitioned from the relatively simple state following the Big Bang to the complex, structured cosmos we observe today. It is in this era that the surprises emerged. The galaxies the telescope found in the light that had travelled all this way were not what the theories had predicted. The light that left before the Earth existed carried a message that astronomers had not anticipated. To understand the message, and why it was so surprising, we need to understand what astronomers had expected to find, and what the number called redshift actually tells us about these ancient objects. The word redshift appears constantly in discussions of distant galaxies, and it is worth understanding clearly because it is the key measurement that tells astronomers how far away, and therefore how old, a galaxy is. The concept is not difficult, but it is easy to hold a vague or mistaken picture of what it means. A clear understanding makes the rest of the story much easier to follow. Redshift refers to the stretching of light's wavelength. Light is a wave, and like any wave, it has a wavelength, the distance between successive peaks of the wave. Different wavelengths of light correspond to different colours. Short wavelengths are toward the blue and violet end of the spectrum. Longer wavelengths are toward the red end. Beyond red, at even longer wavelengths, is infrared, which is invisible to the human eye. The redshift of a galaxy is a measure of how much the wavelength of its light has been stretched on its way to us. There are different physical causes that can stretch light's wavelength. One is motion. If a source of light is moving away from you, its light is stretched to longer wavelengths by the same Doppler effect that lowers the pitch of a receding siren. But the redshift of distant galaxies is caused by something different, the expansion of the universe itself. As light travels through expanding space, the space it travels through stretches, and the light stretches along with it. This is called cosmological redshift, and it is distinct from the ordinary Doppler effect, even though both produce a stretching of wavelength. The amount of redshift is expressed as a number, usually denoted by the letter Z. A redshift of 0 means no stretching. A redshift of 1 means the wavelength has been stretched to twice its original value. The light arrives with a wavelength twice as long as when it was emitted. A redshift of 14, which is roughly the highest measured for confirmed galaxies, means the wavelength has been stretched to 15 times its original value. The relationship is that the stretching factor equals 1 plus the redshift. So redshift 14 means a stretching factor of 15. The redshift can be measured with great precision using spectroscopy. When astronomers split the light from a galaxy into its component wavelengths, they see specific features, bright or dark lines at particular wavelengths, produced by the atoms and molecules in the galaxy. These features occur at known wavelengths in laboratory conditions. By measuring how much the features have been shifted from their laboratory wavelengths, astronomers can calculate the redshift precisely. This is why spectroscopic confirmation is so important. It provides a reliable, precise measurement of the redshift, which can then be converted into a distance and an age. The conversion from redshift to distance and age depends on the cosmological model, on how fast the universe has been expanding throughout its history. Using the standard model, astronomers can convert a measured redshift into the time at which the light was emitted. A redshift of 1 corresponds to light emitted when the universe was about half its current age. A redshift of 6 corresponds to about 1 billion years after the Big Bang. A redshift of 14 corresponds to about 300 million years after the Big Bang, the earliest galaxies yet observed. These conversions are at the heart of how the James Webb Space Telescope studies the early universe. The telescope measures the redshifts of distant galaxies primarily through spectroscopy and converts those redshifts into times. The highest redshift galaxies are the earliest, dating from when the universe was only a few 100 million years old. By studying them, astronomers study the universe at its earliest observable epochs. It is worth emphasizing how high the redshifts of these galaxies are. Before the James Webb Space Telescope, the highest redshift confirmed galaxies were around redshift 11. The telescope pushed this to redshift 14 and beyond within its first few years of operation. Each increment in redshift corresponds to looking further back in time, to an earlier and less developed period of cosmic history. The galaxies at redshift 14 are being observed as they were when the universe was in its earliest chapter of galaxy formation. The redshift, then, is the fundamental measurement. It tells astronomers how far away a galaxy is, how long its light has been travelling, and what epoch of cosmic history they are observing. It is the number that places each galaxy in cosmic time, and it is the foundation for the surprise that the telescope produced. Galaxies at very high redshift, very early in cosmic history, that appeared far more massive and developed than the theories said they should to be. To understand why this was a surprise, we need to look at what the theories actually predicted. Before the James Webb Space Telescope began its observations, astronomers had a well-developed picture of how the early universe should look. This picture was not a guess. It was the product of decades of theoretical work, computer simulations, and observations with earlier telescopes, all combined into a coherent model of how the universe evolved from the Big Bang to the present. The model made specific predictions about what the telescope should find when it looked at the early universe. Those predictions are the baseline against which the actual observations were measured. The standard model of cosmology holds that the universe began about 13.8 billion years ago in an extremely hot, dense state, the Big Bang. In the first moments, the universe was a uniform soup of fundamental particles, with no structure. As the universe expanded and cooled, the particles combined into atoms, primarily hydrogen and helium. For a few 100 million years after this, there were no stars and no galaxies, a period sometimes called the Cosmic Dark Ages. The universe was filled with neutral gas, gradually being pulled together by gravity, but not yet forming luminous structures. According to the model, the first stars and galaxies formed gradually, as gravity slowly assembled the gas into denser and denser concentrations. The process was thought to be slow at first. Small clumps of gas would collapse to form the first stars. These first stars would group into small protogalaxies. The protogalaxies would gradually merge and grow, accumulating mass over hundreds of millions and then billions of years. Large, massive galaxies like the Milky Way were thought to be the end product of this long process of assembly, built up gradually over billions of years through the merging of smaller structures. This gradual hierarchical picture of galaxy formation was central to the Standard Model. It predicted that the earliest galaxies should be small, faint, and not very massive. They should be just beginning the process of assembly, with relatively few stars and modest total masses. The big, massive, fully developed galaxies should appear only later, after enough time had passed for the gradual build-up to occur. In the first few 100 million years after the Big Bang, the model predicted, there should be only small immature galaxies, the seeds from which larger galaxies would eventually grow. The model also predicted how many galaxies of various sizes should exist at each epoch. Using the known physics of gas, gravity, and star formation, combined with the measured properties of the universe, astronomers could calculate the expected number of galaxies of each mass at each redshift. These calculations produced what is called a mass function, a prediction of how many galaxies of each mass should exist at a given time. The mass function for the early universe predicted relatively few massive galaxies and many small ones, consistent with the hierarchical assembly picture. These predictions were tested to a degree with earlier telescopes, including the Hubble Space Telescope. Hubble could see galaxies out to redshifts of about 10 or 11, corresponding to a few 100 million years after the Big Bang. The galaxies it found at those redshifts were generally consistent with the predictions, small, faint, immature. The picture seemed to hold up, at least as far as Hubble could see. The Standard Model appeared to provide a good description of the early universe, within the limits of the available data. But Hubble's view was limited. It could see only the brightest galaxies at the highest redshifts, and even those only faintly. The full population of early galaxies, including fainter ones and ones at even higher redshifts, was beyond Hubble's reach. The detailed testing of the model at the earliest epochs awaited a more powerful telescope. The James Webb Space Telescope was built in part to provide that test. It would see the early universe in far greater detail than Hubble could, revealing the full population of early galaxies and allowing a thorough comparison with the predictions of the Standard Model. Astronomers expected on the whole that the predictions would hold up. They expected to find what the model predicted: a population of small, faint, immature galaxies in the early universe, gradually assembling into larger structures. There would be refinements and surprises, no doubt. There always are. But the basic picture was expected to survive. The Standard Model had been remarkably successful in explaining a wide range of observations, and there was little reason to expect it to fail dramatically when applied to the early universe. This was the universe astronomers expected to find: a slow, gradual, hierarchical assembly of galaxies beginning with small seeds and building up over billions of years. It was a well-motivated expectation, grounded in solid theory and consistent with the available data. And it was, in certain important respects, wrong. The telescope, when it looked, found something different. The galaxies it found in the early universe were not all small and faint and immature. Some of them were big, bright, and surprisingly mature, far more developed than the model said they should be. The first deep observations from the James Webb Space Telescope began arriving in the summer of 2022. Among the early targets were deep field observations, long exposures of small patches of sky designed to capture the faintest and most distant galaxies. These were the observations that would test the predictions of the Standard Model at the earliest epochs. Astronomers around the world examined the data with intense interest. looking for the population of early galaxies that the telescope was uniquely able to reveal. What they found almost immediately was a surprise. The deep field images contained galaxies at very high redshift, galaxies from the early universe as expected. But some of these galaxies appeared far brighter and more massive than the standard model predicted for their epoch. They were not the small, faint, immature Cs that the hierarchical assembly picture called for. They were substantial luminous galaxies, apparently containing large numbers of stars at a time when such galaxies should not yet have had time to form. The initial reaction among astronomers was caution. Extraordinary claims require extraordinary evidence, and the claim that the telescope had found galaxies that contradicted the standard model was certainly extraordinary. There were many possible sources of error. The initial distance estimates for these galaxies were based on photometry, measurements of the galaxy's brightness in different wavelength bands, rather than on spectroscopy, which is more reliable. Photometric redshift estimates can be wrong, sometimes dramatically, if a galaxy's light is misinterpreted. A relatively nearby galaxy with certain properties can masquerade as a distant one in photometric data. So the first task was to confirm the distances. Astronomers used the telescope's spectrographs to obtain spectra of the candidate early galaxies, measuring their redshifts precisely. This was painstaking work, requiring long exposures and careful analysis. But it was essential. Without spectroscopic confirmation, the surprising galaxies might turn out to be measurement errors or misidentified nearby objects. With spectroscopic confirmation, their distances, and therefore their early epochs, would be established beyond reasonable doubt. As the spectroscopic confirmations came in, the surprise deepened. Many of the candidate early galaxies were confirmed to be genuinely at high redshift, genuinely from the early universe. They were not misidentified nearby objects. They were real, distant early galaxies, and they were, in many cases, genuinely more massive and luminous than the standard model predicted. The surprise was not a measurement error. It was a real feature of the early universe, revealed by the telescope's observations. The unease among astronomers grew as more of these galaxies were confirmed. One or two surprising galaxies might be statistical flukes, rare objects that happened to form unusually early. But the telescope was finding many of them. The early universe appeared to be populated with more massive, more luminous galaxies than the model predicted, and in greater numbers. This was not a matter of a few anomalies. It was a systematic discrepancy between the predictions of the standard model and the observations of the telescope. Papers began to appear, documenting the surprising galaxies and discussing their implications. Some of the papers used dramatic language, suggesting that the observations might break the standard model of cosmology, or that they posed a serious challenge to the established picture of galaxy formation. The phrase, "impossible early galaxies," appeared in some discussions. The findings attracted attention not only among specialists, but in the broader scientific press, where the story of a telescope that might have overturned cosmology was naturally appealing. The reality, as is usually the case, was more nuanced than the dramatic headlines suggested. The observations were genuinely surprising and genuinely difficult to reconcile with the standard predictions. But whether they actually broke cosmology, whether they required a fundamental revision of the standard model or merely a refinement of the theories of galaxy formation within that model, was a question that could not be answered immediately. It required careful analysis, additional observations, and a thorough exploration of the possible explanations. That analysis is still ongoing. What was clear, even in those early months, was that the telescope had revealed something unexpected about the early universe. The galaxies it found were not the ones the theories had predicted. Whether this was a minor adjustment or a major revolution remained to be seen. But the unease was real, and it was justified. The universe, as revealed by the telescope, was not quite the universe astronomers had expected. The first images had opened a question that would occupy the field for years to come. The episode also revealed something about how science responds to surprise. The first reaction was not celebration or panic, but careful checking. The slow, unglamorous work of confirming distances, revising estimates, and testing alternatives. Only after that work did the genuine surprise crystallize. This is how good science handles the unexpected, not by leaping to conclusions, but by patiently establishing what is real before deciding what it means. The unease among astronomers was, in its way, a sign of the field working as it should. To understand precisely why these galaxies were so surprising, it helps to be concrete about the problem. The issue was not simply that the galaxies were old. Astronomers expected to find old galaxies in the early universe. The issue was that the galaxies were too developed for how old the universe was when the light left them. They contained too many stars, too much mass assembled too quickly for the standard timeline of galaxy formation to accommodate. Consider what it takes to build a massive galaxy. A galaxy is, at its core, a vast collection of stars bound together by gravity. To build a massive galaxy, you need to form a large number of stars, and forming stars takes time. Gas must collect into dense clouds. The clouds must collapse under their own gravity. The collapse must proceed to the point where nuclear fusion ignites, producing a star. This process, repeated billions of times, builds up the stellar population of a galaxy. And the whole thing takes time. Time for the gas to collect, time for it to collapse, time for the stars to form. The standard model assumed that this process proceeded at a certain rate, governed by the merest known physics of gas, gravity, and star formation. At that rate, building a massive galaxy, one containing tens or hundreds of billions of stars, should take a long time, on the order of billions of years. The massive galaxies we see in the nearby universe, like the Milky Way, were thought to have been assembled gradually over most of cosmic history, growing slowly as gas accumulated and stars formed, and smaller structures merged together. The problem with the James Webb observations was that they showed massive galaxies existing when the universe was only a few 100 million years old. There simply had not been enough time, according to the standard rate of star formation, to build such massive galaxies so quickly. The galaxies appeared to contain more stars than could have formed in the available time, given the assumed rate of star formation. It was as if the galaxies had assembled themselves faster than the physics allowed. The mismatch can be quantified. Astronomers can estimate the mass of stars in a galaxy from its brightness and colour. They can estimate the available gas from the mass of the galaxy's dark matter halo, using the known ratio of ordinary matter to dark matter. And they can calculate what fraction of that gas would have had to convert into stars to produce the observed stellar mass in the available time. For some of the surprising galaxies, this fraction approached 100%, meaning essentially all of the available gas would have had to convert into stars, with no waste and no delay. This is a problem, because star formation is not perfectly efficient. In the nearby universe, only a small fraction of the available gas converts into stars. The rest is blown away by stellar winds, heated by radiation, or otherwise prevented from forming stars. Typical star formation efficiencies are a few percent to perhaps 10 or 20%. An efficiency approaching 100% would be unprecedented, far higher than anything observed in the nearby universe, and far higher than the standard model assumed. The surprising galaxies seem to require this impossibly high efficiency, or else some other explanation. This is what astronomers meant when they said the galaxies should not exist yet. Given the standard assumptions about how galaxies form and how fast stars form, there should not have been enough time to build such massive galaxies so early. The galaxies existed nonetheless. Something about the standard assumptions had to be wrong, either the rate of star formation, or the amount of available gas, or the conversion efficiency, or some deeper aspect of the model. It is important to be precise about what kind of problem this was. It was not, at least initially, a problem with the fundamental cosmological model, how the universe expands, how much matter it contains, how structure grows under gravity. It was a problem with the theories of galaxy formation, which describe how gas turns into stars within that framework. These theories are less fundamental and less well established than the underlying cosmology. They involve complicated physics, gas dynamics, star formation, feedback from stars and black holes that is difficult to model. It was quite possible that the surprising galaxies indicated a problem with these galaxy formation theories rather than with the fundamental cosmology. But it was also possible that the problem ran deeper. If the galaxies were massive enough, and early enough and numerous enough, they might exceed what the fundamental cosmology could provide, regardless of the details of galaxy formation. There is a limit to how much matter is available to form galaxies at a given epoch, set by the cosmological model. If the observed galaxies contained more mass than that limit allowed, the problem would be with the cosmology itself, not just with the theories of galaxy formation. Determining which kind of problem the observations represented was, and remains, a central question. The phrase that came to capture the surprise was too big, too soon. The galaxies the telescope found in the early universe were too big, too massive, containing too many stars, and appeared too soon, at too early an epoch, for the standard timeline to accommodate. This phrase, or variations of it, appeared repeatedly in the scientific discussions of the findings. It captured the essence of the problem succinctly. The too soon part is a direct consequence of the high redshifts. The galaxies were observed at redshifts above 10 and some above 14, corresponding to times only a few 100 million years after the Big Bang. This is very early in cosmic history. The universe was only about 2% of its current age. The Standard Model predicted that galaxies at this epoch should be small and immature. Finding massive, developed galaxies instead was finding them too soon. The too big part refers to the masses of the galaxies. Astronomers estimated the stellar masses of the surprising galaxies from their brightness and colour, and found that some of them contained billions or even tens of billions of solar masses worth of stars. For comparison, the Milky Way contains a few 100 billion solar masses of stars, built up over more than 13 billion years. To find galaxies with a substantial fraction of the Milky Way's stellar mass, already in place just a few 100 million years after the Big Bang, was to find galaxies that were too big for their age. The combination of too big and too soon is what created the tension with the Standard Model. Either feature alone might have been accommodated. Massive galaxies are expected eventually, just not so early. Early galaxies are expected, just not so massive. It was the combination of large mass and early epoch that created the problem. The galaxies had assembled too much mass too quickly, faster than the Standard Model's timeline of gradual assembly allowed. Several specific galaxies became prominent examples of the problem. Early in the telescope's operations, a set of candidate massive galaxies at high redshift was identified, with estimated masses that seemed to strain or exceed what the Standard Model could accommodate. These candidates attracted intense scrutiny. Some were later found, upon spectroscopic examination, to be at lower redshifts than initially estimated, or to have lower masses, reducing the tension. Others held up under scrutiny, remaining genuinely massive and genuinely early. The process of scrutiny was important. The initial mass and redshift estimates were uncertain, based on limited data. As more data was gathered and more careful analysis was performed, some of the apparent anomalies diminished. A galaxy that initially appeared impossibly massive might, on closer examination, turn out to be somewhat less massive or somewhat less early, bringing it back within the bounds of what the model could accommodate. This is the normal process of science. Initial surprising results are refined and sometimes revised as better data accumulates. But not all of the anomalies went away. After the dust settled on the initial round of scrutiny, there remained a population of galaxies that were genuinely more massive, and genuinely earlier than the Standard Model comfortably predicted. The tension was reduced from the initial dramatic claims, but it was not eliminated. The early universe really did seem to contain more massive galaxies, formed more quickly than the model anticipated. The problem of too big too soon was real, even if it was less severe than the most dramatic early reports suggested. The persistence of the tension, even after careful scrutiny, is what made it scientifically significant. If all the anomalies had disappeared upon closer examination, the episode would have been a cautionary tale about the dangers of premature claims based on preliminary data. Instead, a real discrepancy remained, demanding explanation. The early universe was forming massive galaxies faster than the standard theories predicted. Something was going on that the theories did not fully capture. The question then was what? What allowed the early universe to form massive galaxies so quickly? Was it a matter of more efficient star formation than expected? A different population of stars in the early universe? A larger amount of available gas? A flaw in the fundamental cosmology? Or some combination of these? These questions drove the research that followed the initial discoveries. They are in large part still open. The telescope had revealed a real puzzle. Solving it would require understanding the early universe in more detail than ever before, and possibly revising some long-held assumptions about how galaxies, and perhaps the universe itself, actually work. The phrase too big too soon thus stands as a compact label for one of the most important findings of the telescope's early years. It marks the point where observation outran theory, where the universe revealed itself to be doing something our models had not anticipated. Behind those 4 words lies a genuine scientific puzzle, one that continues to occupy researchers and to drive new observations and new ideas. Among the many distant galaxies that the James Webb Space Telescope discovered, one became for a time the most famous. A galaxy designated JADES-GS-Z 14-0. Its name encodes its origins. JADES stands for the JWST Advanced Deep Extragalactic Survey, one of the major observing programs designed to study the early universe. GS refers to the Goods South Field, a particular patch of sky that has been studied intensively by many telescopes. The Z14 indicates its redshift, approximately 14. The galaxy held, for a period, the record as the most distant, and therefore the earliest galaxy ever confirmed. The galaxy was first identified in imaging data as a candidate high redshift object in observations made in 2023. Its appearance in the images suggested that it might be at very high redshift. But as with all such candidates, the photometric estimate had to be confirmed spectroscopically. The team obtained a spectrum using the telescope's near-infrared spectrograph, and the spectrum confirmed a redshift of approximately 14.3. This corresponded to a time only about 290 million years after the Big Bang, when the universe was about 2% of its current age. The confirmation made JADES-GS-Z14-0 the most distant galaxy with a spectroscopically confirmed redshift at the time of its announcement in 2024. But its distance was not the only remarkable thing about it. The galaxy was also surprisingly luminous and surprisingly large. Measurements indicated that it was over 1,600 light-years across, a substantial size for such an early galaxy, and its brightness implied that it contained a significant mass of stars, on the order of hundreds of millions of solar masses. The size and brightness of the galaxy carried an important implication. In many distant galaxies, much of the light comes from material falling into a central supermassive black hole, producing an intensely bright region called a quasar. If JADES-GS-Z 14-0's light had come from such a source, its brightness would not necessarily indicate a large stellar mass. But the galaxy was too extended, too large in physical size, for its light to come from a compact central source. The light had to come from stars, distributed across the galaxy's substantial size. This meant the galaxy genuinely contained a large mass of stars, formed in the first 290 million years of cosmic history. This was a significant finding. A galaxy with hundreds of millions of solar masses of stars already in place, 290 million years after the Big Bang, was a challenge to the standard timeline of galaxy formation. It implied that star formation in the early universe had proceeded quickly enough to build a substantial galaxy in a short time. The galaxy was a concrete, specific example of the too big, too soon problem, with a spectroscopically confirmed redshift that put its early epoch beyond doubt. Astronomers studied the galaxy in further detail. Observations with the telescope's mid-infrared instrument detected the galaxy at longer wavelengths, providing additional information about its properties. The data suggested that the galaxy contained perhaps 500 million solar masses of stars, with a strong burst of star formation in the few million years before the observed epoch. The presence of certain emission features in the galaxy's light indicated the presence of oxygen, which is significant because oxygen is produced by stars and dispersed when they die. The presence of oxygen so early implied that multiple generations of stars had already lived and died in the galaxy, enriching it with elements heavier than the hydrogen and helium that the universe started with. This was perhaps the most striking aspect of JADES-GS-Z 14-0. The presence of oxygen meant that the galaxy was not made purely of primordial gas. It had already undergone significant chemical evolution. Stars had formed, lived, died, and dispersed their products into the galaxy, and new stars had formed from the enriched gas. This kind of chemical evolution takes time. Multiple generations of stars must live and die. To find it so early in a galaxy observed just 290 million years after the Big Bang was to find that the processes of stellar and chemical evolution had begun even earlier, in the first chapters of cosmic history. JADES-GS-Z 14-0 thus became an emblem of the surprises the telescope had revealed. It was distant, early, large, luminous, massive, and chemically evolved, all the things the Standard Model said an early galaxy should not yet be. It was a single concrete example of the broader pattern. the early universe forming galaxies more quickly and more fully than the theories predicted. For a time, it was the most distant confirmed galaxy known, the current edge of our observations of cosmic time, and it would not hold that record for long. The telescope kept looking, and it kept finding galaxies even further away, even earlier, even more surprising. Section 9, 800, 2 words. Section 10, 290 million years after everything began. It is worth dwelling on what 290 million years after the Big Bang actually means, because the number is easy to state but hard to grasp. The universe is currently about 13.8 billion years old. 290 million years is about 2% of that. If we compress the entire history of the universe into a single calendar year, with the Big Bang on January 1st and the present moment on December 31st, then 290 million years after the Big Bang corresponds to about January 7th or 8th. JADES-GS-Z14-0 is being observed as it was in the first week of the cosmic year. In that first week of cosmic time, a great deal had to happen for a galaxy like JADES-GS-Z14-0 to exist. The universe had to expand and cool from its initial hot, dense state. The first atoms had to form. The cosmic dark ages had to pass, during which gravity slowly pulled the primordial gas into denser concentrations. The first stars had to ignite. Those first stars had to live, die, and disperse their products. New stars had to form from the enriched gas. Enough stars had to accumulate to build a galaxy with hundreds of millions of solar masses. All of this had to happen in 290 million years. To appreciate how short a time this is, consider that the Sun takes about 230 million years to complete a single orbit around the centre of the Milky Way. The entire history of the galaxy, JADES-GS-Z14-0, from the Big Bang to the moment we observe it, is only slightly longer than one orbit of the Sun around our galaxy. In that brief span, an entire galaxy formed, with multiple generations of stars and significant chemical enrichment. The pace of development was extraordinary. Compare this to the history of life on Earth. The Earth is about 4.5 billion years old. Complex animal life has existed for perhaps the last 600 million years. The galaxy JADES-GS-Z14-0 formed in its entirety in about half the time that complex life has existed on Earth. The processes of cosmic structure formation in the early universe operated on timescales that were short compared to the timescales of biological evolution that we are more familiar with. The shortness of the time is precisely what makes the galaxy so surprising. The standard model allowed for galaxies to form in the early universe, but it expected them to be small and immature at 290 million years, just beginning the long process of assembly. To find a substantial chemically evolved galaxy at that epoch was to find that the assembly had proceeded much faster than expected. The universe had built a real galaxy in the first week of its cosmic year, when the theories said it should still be assembling the raw materials. There is a deeper point here about the nature of cosmic time. The early universe was a different place, operating under different conditions than the universe we inhabit today. It was denser, gas was more abundant and more concentrated. The conditions for rapid star formation may have been more favourable than they are now. Processes that take a long time in the present universe might have proceeded more quickly in the dense, gas-rich conditions of the early cosmos. The surprising speed of early galaxy formation may reflect these different conditions, rather than any flaw in the fundamental physics. This is one of the leading ideas for explaining the surprising galaxies. That star formation in the early universe was simply more efficient than in the present universe, because the conditions were different. The dense, gas-rich early universe may have been able to convert gas into stars more rapidly and more completely than the present universe can. If so, the surprising galaxies would not require any new physics, just a recognition that the early universe was a more efficient star-forming environment than the standard models assumed. But this idea, while promising, is not yet fully established. It requires that star formation efficiency in the early universe was substantially higher than in the present universe, and the reasons for this higher efficiency are not fully understood. There are physical arguments for why the early universe might form stars more efficiently, but turning those arguments into a quantitative model that matches the observations is ongoing work. The idea is plausible, but it has not yet been demonstrated conclusively. What is clear is that 290 million years after the Big Bang, The universe already contained galaxies more developed than the standard model expected. Whatever the explanation, more efficient star formation, a different population of early stars, or something deeper, the early universe was busier, faster, and more productive than the theories had anticipated. The first week of the cosmic year was not a quiet period of slow assembly. It was a period of rapid, vigorous galaxy formation, producing substantial galaxies in a remarkably short time. The telescope had revealed an early universe that was more active than anyone had expected. JADES-GS-Z 14-0 did not hold the record for the most distant galaxy for very long. In science, records of this kind are made to be broken, and the James Webb Space Telescope kept looking deeper into cosmic time. In 2025, astronomers announced a new record holder, a galaxy designated MOM-Z14, with a redshift of approximately 14.4, slightly higher than JADES-GS-Z14-0, corresponding to a time about 280 million years after the Big Bang. The galaxy's name, like JADES-GS-Z14-0, encodes information about its discovery. The Z14 again refers to its redshift of approximately 14. The galaxy was identified and confirmed through the telescope's observations, and its redshift was measured spectroscopically, establishing it as the new most distant confirmed galaxy. The study reporting it was initially released as a preprint in 2025 and was subsequently peer-reviewed and published, confirming the finding through the normal process of scientific scrutiny. MOM-Z14 has some properties that distinguish it from JADES-GS-Z14-0. It is more compact, only about 240 light-years across, considerably smaller than JADES GSZ-0's 1,600 light-years. It contains roughly as much mass as the Small Magellanic Cloud, a dwarf galaxy that orbits the Milky Way. In this sense, MOM-Z14 is a smaller galaxy than JADES GSZ-0, even though it is slightly more distant and slightly earlier. The two galaxies are different in their detailed properties, even though they are both extremely early and both record-setting in their distance. One intriguing feature of MOM-Z14 is its chemical composition. The galaxy is rich in nitrogen relative to carbon, a pattern that resembles the composition of certain globular clusters observed in the Milky Way. Globular clusters are dense, ancient collections of stars, among the oldest objects in our galaxy. The chemical similarity between MOM-Z14 and these ancient clusters hints at a possible connection between the earliest galaxies and the oldest stellar populations we observe nearby. It is a tantalizing clue about how the structures of the early universe relate to the structures we see around us today. Like JADES-GS-Z14-0, MOM-Z14 was observed during a burst of rapid star formation. This is a recurring theme among the early galaxies that the telescope has found. They are frequently caught in the act of forming stars rapidly, in intense bursts. This may be partly a selection effect. Galaxies forming stars rapidly are brighter and easier to detect, so they are overrepresented among the galaxies we find. But it may also reflect a genuine feature of the early universe, where rapid bursty star formation was common. The early galaxies were not forming stars at a slow, steady pace. They were forming them in rapid bursts, building up their stellar masses quickly. The breaking of the distance record from JADES-GS-Z14-0 to MOM-Z14 illustrates an important point about the telescope's ongoing work. The telescope has not found a single anomalous galaxy and stopped. It has found a growing population of early galaxies, and it continues to push the boundary of what can be observed to earlier and earlier epochs. Each new record holder is slightly more distant, slightly earlier than the last. The boundary of our observations keeps moving back toward the Big Bang, and each step reveals more about the earliest chapters of cosmic history. This ongoing progress is part of what makes the situation scientifically rich. If the telescope had found one surprising galaxy and nothing else, the finding could be dismissed as a fluke. But it is finding many surprising galaxies across a range of redshifts, and it keeps finding them as it looks deeper. The pattern is robust. The early universe really does contain a population of galaxies that formed quickly and grew substantial early. The accumulation of examples, including new record holders like MOM-Z14, strengthens the case that this is a real feature of the cosmos, not an artifact of a few unusual objects. The records will likely continue to break. The telescope has not yet reached the limit of what it can observe. There may be galaxies at even higher redshifts, even earlier epochs waiting to be found. Each one will push the boundary back further and provide more information about the earliest galaxies. The team that found JADES-GS-Z 14-0 suspected, even at the time that other candidates awaiting confirmation might be at higher redshifts. MOM-Z14 confirmed that suspicion. There may be more to come. Each new discovery refines our understanding of the early universe and sharpens the question of how these early galaxies formed so quickly. The record breaking is not just a matter of setting new marks for their own sake. It is a matter of pushing our observations closer and closer to the beginning, gathering more data about the crucial early epochs when the first galaxies formed. The closer we get to the Big Bang, the more we learn about how the structured universe we inhabit emerged from the simple, uniform state that followed the cosmic beginning. In late 2024, a study published in the journal Nature added a striking new chapter to the story. An international team of astronomers, using the James Webb Space Telescope, identified 3 ultra-massive galaxies in the early universe, each nearly as massive as the Milky Way, already in place within the first billion years after the Big Bang. The team gave these galaxies a memorable nickname, the Red Monsters. The name captured both their appearance. They are red because their light is heavily redshifted, and their surprising nature as monstrously massive galaxies that should not have existed so early. The red monsters were significant because of their extreme masses. Each of the 3 galaxies contained a stellar mass comparable to that of the Milky Way, on the order of 100 billion solar masses. The Milky Way took more than 13 billion years to assemble that mass. The red monsters apparently did it in less than a billion years. This was the too big, too soon problem in its most extreme form. Galaxies as massive as our own, fully assembled when the universe was less than a tenth of its current age. The study's analysis indicated that these galaxies had converted an unusually large fraction of their available gas into stars. Recall that in the nearby universe, star formation is inefficient. Only a small fraction of the available gas becomes stars. The red monsters appeared to have converted a much larger fraction, perhaps approaching half of their available gas, into stars. This high efficiency allowed them to build up their large masses quickly in the limited time available in the early universe. The findings suggested that star formation in these early galaxies was far more efficient than in galaxies today. The discovery was made possible by the telescope's spectroscopic capabilities at near-infrared wavelengths. The spectra allowed the team to confirm the distances of the galaxies and to estimate their masses and star formation properties. Without spectroscopy, the galaxies might have been dismissed as misidentified nearby objects. With spectroscopy, their early epochs and large masses were established with confidence. The red monsters were real, and they were genuinely massive and genuinely early. The team was careful to note that the findings did not necessarily conflict with the fundamental cosmological model. The masses of the red monsters, while large, did not clearly exceed what the cosmology could provide, the amount of matter available to form galaxies at that epoch. Instead, the findings challenged the theories of galaxy formation, specifically the assumption about how efficiently gas converts into stars. If star formation in the early universe was much more efficient than assumed, the red monsters could be accommodated within the standard cosmology without requiring new fundamental physics. The challenge was to the details of galaxy formation, not necessarily to the cosmological framework itself. This distinction between a challenge to galaxy formation theory and a challenge to fundamental cosmology is crucial, and it recurs throughout the discussion of the James Webb findings. The surprising galaxies clearly indicate that something about our theories is incomplete. But whether the incomplete part is the relatively detailed and uncertain theory of galaxy formation, or the more fundamental and well-established theory of cosmology, is the key question. The red monsters, according to their discoverers, pointed to the former, a need to revise our understanding of how efficiently early galaxies formed stars, rather than a need to overturn the cosmological model. Still, the red monsters intensified the puzzle. 3 galaxies as massive as the Milky Way, in the first billion years, required star formation efficiencies far higher than anything seen in the present universe. Why was the early universe so much more efficient at forming stars? What physical conditions allowed such rapid, complete conversion of gas into stars? These questions did not have settled answers. The red monsters were a vivid demonstration that the early universe operated differently from the present universe in ways that the standard theories had not anticipated. The name red monsters reflects a certain playfulness in how astronomers talk about their discoveries, but the objects themselves are serious scientific puzzles. They sit at the extreme end of the population of surprising early galaxies, the most massive and most challenging examples. They demonstrate more dramatically than any other objects that the early universe was capable of forming massive galaxies with surprising speed. And they sharpen the central question raised by all of the James Webb findings. What allowed the early universe to build galaxies so much faster than we expected? The team that found the red monsters concluded that future observations would provide further insight. Additional studies with the James Webb Space Telescope and with other instruments such as the Atacama Large Millimeter Array would reveal more about these ultramassive early galaxies and would find larger samples of such objects. As the sample grows, astronomers will be better able to characterize the population of early massive galaxies and to test the various explanations for their rapid formation. The red monsters were not the end of the story. They were a striking new piece of a puzzle that is still being assembled. To make sense of the claim that certain galaxies are too massive, it helps to understand where the limit comes from. What sets the boundary between a galaxy that the model can accommodate and one that it cannot? The limit is not arbitrary. It is rooted in the fundamental properties of the universe, in the amount of matter available to form galaxies at any given epoch. Understanding this limit clarifies what kind of problem the surprising galaxies pose. The universe contains two main kinds of matter: ordinary matter, made of atoms, which forms stars and planets and everything we can see, and dark matter, which does not emit light and is detected only through its gravity. Dark matter is more abundant than ordinary matter by a factor of about 5. For every gram of ordinary matter, there are about 5 grams of dark matter. This ratio is well measured from observations of the cosmic microwave background and other cosmological data. It's one of the fundamental parameters of the Standard Model. In the standard picture of structure formation, galaxies form within concentrations of dark matter called halos. The dark matter, being more abundant, dominates the gravity. It pulls together into halos under its own gravity, and the ordinary matter, the gas, falls into these halos and forms stars. The mass of stars a galaxy can contain is therefore limited by the amount of ordinary matter available in its dark matter halo, which is in turn limited by the size of the halo and the cosmic ratio of ordinary to dark matter. This sets an upper limit on how massive a galaxy can be at a given epoch. The dark matter halos grow over time as gravity assembles more and more dark matter into larger and larger concentrations. At early times, the halos are small because there has not been time for large ones to form. A small halo contains a limited amount of dark matter and therefore a limited amount of ordinary matter, and therefore can form only a limited mass of stars. The maximum possible stellar mass at a given epoch is set by the largest halos that exist at that epoch, multiplied by the fraction of ordinary matter, multiplied by the fraction of that ordinary matter that has turned into stars. The absolute upper limit, then, assumes that every bit of ordinary matter in the largest available halo has been converted into stars. A star formation efficiency of 100%. This is the theoretical maximum. No galaxy can contain more stellar mass than this, because there simply is not more ordinary matter available in the halo. If a galaxy is observed to contain more stellar mass than this absolute limit allows, then there is a genuine problem with the fundamental cosmology. The model cannot provide enough matter to make such a galaxy. The initial reports of surprising James Webb galaxies suggested, in some cases, that the galaxies approached or even exceeded this absolute limit. This was what generated the most dramatic claims that the telescope might have broken cosmology. If a galaxy genuinely contained more stellar mass than the largest possible halo could provide, the standard cosmology would be in serious trouble. This was the alarming possibility raised by the early observations. But as the analysis was refined, the situation became less alarming. The mass estimates for the surprising galaxies were uncertain, and as better data accumulated, many of the masses were revised downward. The star formation efficiencies required, while high, were generally found to be below 100%, perhaps 30 to 50% for the most extreme cases, rather than the impossible 100% that the initial estimates had suggested. A star formation efficiency of 30 to 50% is much higher than in the present universe, but it is not physically impossible. It does not exceed the absolute limit set by the cosmology. This refinement was important. It moved the problem from the realm of the cosmology is broken to the realm of galaxy formation is more efficient than we thought. A star formation efficiency of 30 to 50% is surprising and requires explanation, but it does not require new fundamental physics. It requires a revision of the theories of galaxy formation, an acknowledgement that the early universe converted gas into stars more efficiently than the standard models assumed. This is a significant revision, but it is not a revolution in our understanding of the universe. So how massive is too massive? The answer depends on what you mean. If you mean more massive than the standard galaxy formation models predicted, then many of the James Webb galaxies are too massive. They require unexpectedly high star formation efficiencies. But if you mean more massive than the fundamental cosmology can provide, then most of the galaxies, on careful analysis, are not too massive. They stay below the absolute limit, requiring high but not impossible efficiencies. The distinction is the difference between a puzzle about galaxy formation and a crisis in cosmology. Current evidence points more toward the puzzle than the crisis, though the puzzle remains genuinely unsolved. The central mystery of the surprising galaxies comes down to the speed of star formation. The galaxies contain large masses of stars formed in short times, which requires that stars formed rapidly in the early universe. The question is how rapidly, and whether the required speed is physically possible. Understanding the process of star formation and what might make it faster in the early universe is key to resolving the puzzle. Star formation begins with gas, primarily hydrogen, the most abundant element in the universe. For stars to form, the gas must collect into dense clouds and then collapse under its own gravity. As a cloud collapses, it fragments into smaller pieces, each of which continues to collapse. When a fragment becomes dense and hot enough at its center, nuclear fusion ignites, and a star is born. The process is governed by the interplay of gravity, which pulls the gas together, and various forms of pressure and energy, which resist the collapse. In the present universe, star formation is slow and inefficient. Several factors work against it. Radiation from existing stars heats the gas and pushes it apart. Supernova explosions blast gas out of star-forming regions. Magnetic fields and turbulence resist the collapse of gas clouds. The net result is that only a small fraction of the available gas in a galaxy converts into stars over any given period. The rest remains as gas or is blown away, or is heated to temperatures too high for star formation. This inefficiency is why galaxies in the present universe form stars at relatively modest rates. The surprising James Webb galaxies seem to have formed stars much faster and more efficiently. The question is what was different about the early universe that allowed this? Several possibilities have been proposed, and they are not mutually exclusive. Several factors might have combined to make early star formation more efficient. One possibility is that the early universe was denser. Because the universe has been expanding, it was more compact in the past. Gas was packed more tightly. Denser gas collapses more readily under gravity, because the gravitational forces are stronger when matter is closer together. The higher density of the early universe might have allowed gas to collapse into stars more quickly, increasing the rate and efficiency of star formation. This is a natural consequence of cosmic expansion, and it does not require any new physics. Another possibility involves the nature of the first stars. The very first stars in the universe formed from pristine gas, containing only hydrogen and helium, with none of the heavier elements that later stars contain. Pristine gas behaves differently from enriched gas when it collapses. It may form more massive stars, and it may form them more efficiently, because the absence of heavy elements changes how the gas cools and collapses. If the early galaxies contained a population of these massive, efficiently formed first-generation stars, it might help explain their rapid growth and high luminosity. A third possibility involves the feedback processes that normally limit star formation. In the present universe, radiation and supernovae from young stars push back against further star formation, limiting how many stars can form. But in the early universe, these feedback processes might have been less effective, for various reasons related to the different conditions. If feedback was weaker, more of the available gas could convert into stars before being heated or blown away, increasing the efficiency of star formation. This is a subject of active research, with various models exploring how feedback operated in the early universe. These possibilities, higher density, a different population of first stars, weaker feedback, could combine to make early star formation substantially more efficient than star formation today. If the combined effect was large enough, it could explain the surprising galaxies without requiring any new fundamental physics. The galaxies would be massive and early because the early universe was simply better at forming stars, for reasons rooted in its different physical conditions. The challenge is to turn these qualitative possibilities into quantitative models that match the observations. It is one thing to say that the early universe might have formed stars more efficiently. It is another to build a detailed model that predicts exactly how efficient the star formation was, and to verify that this model matches the masses, luminosities, and numbers of the observed galaxies. This quantitative work is ongoing. The qualitative possibilities are promising, but the detailed models are still being developed and tested. What is clear is that star formation in the early universe ran faster than the standard models assumed. Whether it ran at an impossible speed depends on the standard you use. It ran faster than the standard galaxy formation models predicted, certainly, but it probably did not run faster than the laws of physics allow, given the different conditions of the early universe. The speed was surprising, but likely not impossible. A puzzle to be solved by better models of early star formation, rather than a sign that the fundamental physics is wrong. To understand what it would mean for the James Webb observations to break cosmology, we need to understand what the standard model of cosmology actually is. The model has a name, lambda CDM. It is the framework that has guided cosmology for the past few decades, and it has been remarkably successful in explaining a wide range of observations. Understanding its main features clarifies what is at stake in the debate over the surprising galaxies. The name lambda CDM has two parts. Lambda refers to the cosmological constant represented by the Greek letter lambda, which describes the dark energy that is causing the expansion of the universe to accelerate. CDM stands for cold dark matter, the form of dark matter assumed in the model. Together, these two components, dark energy and cold dark matter, along with ordinary matter, make up the contents of the universe according to the model. The model describes how these components evolve and interact over cosmic history. According to lambda CDM, the universe is composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. Ordinary matter is the stuff of stars, planets, and people. Dark matter is the invisible matter that dominates the gravity of galaxies and galaxy clusters. Dark energy is the mysterious component driving the accelerating expansion of the universe. These proportions are measured from various cosmological observations and are among the fundamental parameters of the model. The model describes the evolution of the universe from a hot, dense beginning, the Big Bang, through expansion and cooling, the formation of atoms, the growth of structure under gravity, and the eventual formation of stars, galaxies, and larger structures. It is a comprehensive framework, accounting for the universe's expansion history, the formation of cosmic structure, the abundances of the light elements produced in the Big Bang, and the properties of the cosmic microwave background. Across all of these domains, lambda CDM has been strikingly successful. The cosmic microwave background is perhaps the model's greatest triumph. This is the oldest light in the universe, released about 380,000 years after the Big Bang, when the universe became transparent. It has been measured in exquisite detail by several space missions. The patterns in this ancient light, the tiny variations in temperature across the sky, encode information about the early universe and the cosmological parameters. Lambda CDM predicts these patterns with remarkable precision, matching the observations to a high degree of accuracy. This success is a major reason the model is so widely accepted. The model also successfully explains the large-scale structure of the universe, the way galaxies are distributed in a vast cosmic web of filaments and voids. Computer simulations based on lambda CDM produce structures that closely resemble the observed distribution of galaxies. The model accounts for how this structure grew from the tiny initial variations seen in the cosmic microwave background, through billions of years of gravitational evolution. This is another major success, demonstrating the model's ability to describe the universe across vast scales and times. Given these successes, cosmologists have strong reasons to trust lambda CDM. It is not a tentative or poorly tested idea. It is a well-established framework, supported by multiple independent lines of evidence, that has passed many stringent tests. Overturning it would require extraordinary evidence evidence that the model fails in some fundamental way that cannot be accommodated by adjusting the details. This is why the claim that the James Webb observations might break lambda CDM was so striking, and why it was met with appropriate skepticism. It is important to distinguish between the fundamental cosmological model, lambda CDM, describing the universe's composition, expansion, and structure formation, and the theories of galaxy formation that operate within it. Galaxy formation theory describes how gas turns into stars within the dark matter halos that lambda CDM provides. This theory is much less fundamental and much less well established than lambda CDM itself. It involves complicated, poorly understood physics, gas dynamics, star formation, feedback that is difficult to model. A failure of galaxy formation theory would not threaten lambda CDM. It would simply mean that the details of how galaxies form need revision. The surprising James Webb galaxies, as we have discussed, most likely indicate a problem with galaxy formation theory rather than with lambda CDM itself. The galaxies require more efficient star formation than the standard galaxy formation models assumed, but they do not clearly exceed what lambda CDM can provide. This means that lambda CDM, the fundamental model, probably survives the challenge, though galaxy formation theory, the less fundamental part, needs revision. But this is not certain, and some researchers have explored whether the observations might point to problems with lambda CDM after all. That possibility and the related Hubble tension is where the story takes a deeper turn. Lambda CDM, combined with the standard theories of galaxy formation, made specific predictions about the first billion years of cosmic history. These predictions are what the James Webb Space Telescope tested, and understanding them in detail clarifies exactly where the observations diverged from expectations. The predictions concern the number, mass, and properties of galaxies at various early epochs. The fundamental prediction was that structure forms hierarchically, small things first, large things later. In the early universe, gravity would have assembled the first small concentrations of dark matter into small halos. Gas would have fallen into these small halos and formed the first stars and small galaxies. Over time, the small halos would have merged into larger ones, and the small galaxies into larger galaxies. The massive galaxies we see today would have been built up gradually, through this long process of merging and accretion over most of cosmic history. This hierarchical picture predicted that the earliest galaxies should be small. At a few 100 million years after the Big Bang, the dark matter halos would still be small, because there had not been time for large ones to form. The galaxies within them would correspondingly be small, containing relatively few stars. Massive galaxies, requiring large halos, should not yet exist in significant numbers. The first billion years should be dominated by small, low-mass galaxies, just beginning the long process of growth. The model also predicted how the number of galaxies of each mass should change over time, the evolution of the galaxy mass function. At early times, there should be very few massive galaxies and many small ones. As time passed, the number of massive galaxies should grow as the hierarchical assembly built them up. The rate of this growth was predicted by the model based on the rate at which dark matter halos grow and the rate at which gas converts into stars within them. In particular, the model predicted that the number of massive galaxies should drop off steeply at early times. Going back in cosmic history, the number of massive galaxies should decline rapidly because there was progressively less time for them to have formed. At a few 100 million years after the Big Bang, massive galaxies should be extremely rare, far rarer than at later epochs. This steep decline in the number of massive galaxies toward early times was a specific quantitative prediction of the model. The James Webb observations contradicted this prediction. The telescope found more massive galaxies at early times than the model predicted. The decline in their number toward early times was less steep than expected. There were too many massive galaxies early on, in addition to the individual galaxies being too big. Both the number and the mass of early galaxies exceeded the predictions. The galaxy mass function at early times did not match what the model said it should be. The model also predicted the brightness of early galaxies, how much ultraviolet light they should emit, which is a measure of their rate of star formation. The James Webb observations found that early galaxies were brighter, in the ultraviolet, than predicted. There were more bright galaxies at early times than the model anticipated. This is closely related to the mass discrepancy. Brighter galaxies generally indicate more rapid star formation and larger stellar masses. The excess of bright early galaxies is another manifestation of the same underlying surprise. These discrepancies, too many massive galaxies, too much brightness, too early, are the quantitative core of the James Webb puzzle. They are not vague impressions, they are specific mismatches between the predicted and observed properties of early galaxies, measured and documented in the scientific literature. The predictions came from lambda CDM combined with standard galaxy formation theory. The observations came from the telescope. The two did not match in specific quantifiable ways. The size of the mismatch is important. If the observed galaxies had exceeded the predictions by just a little, the discrepancy might be attributed to measurement uncertainties or minor errors in the predictions. But the observed excess was substantial. In some cases, the observed number of bright early galaxies exceeded the prediction by a large factor. This large mismatch is what made the finding significant. It was not a minor adjustment. It was a real substantial discrepancy that demanded explanation. Where exactly the explanation lies, in the details of galaxy formation or in the fundamental cosmology, is the question that the next sections explore. It is worth pausing on how unusual this situation is. For most of its history, the Standard Model had a remarkable track record of predicting observations correctly. When new instruments looked at the universe, they generally found what the model said they would find. The James Webb observations broke this pattern, at least for early galaxies. The model predicted one thing, and the telescope saw another. That kind of clear, quantified mismatch between a successful model and a powerful new instrument is precisely the situation that drives science forward, forcing theorists to reckon with data that does not fit. The gap between what lambda CDM predicted and what the James Webb Space Telescope observed is the heart of the matter. Understanding the nature of this gap, its size, its robustness, and its possible interpretations is essential to assessing whether cosmology was truly broken or merely challenged. The gap is real, but its meaning is subtle, and it has been the subject of intense investigation. The first question about any such gap is whether it is real or an artifact of measurement error. Astronomical measurements of distant galaxies are difficult and uncertain. The masses, distances, and brightnesses of these faint remote objects are hard to determine precisely. It was possible in principle that the apparent gap was due to systematic errors in the measurements, that the galaxies were not really as massive or as early as they appeared, and that better measurements would close the gap. This possibility was taken seriously, and a great deal of effort went into checking the measurements. As we have discussed, some of the initial gap did close upon better measurement. Spectroscopic confirmation revised some redshifts, and more careful analysis revised some masses downward. The most extreme initial claims, galaxies that seemed to require impossible star formation efficiencies, were softened as the data improved. This is the normal process of science. Initial surprising results are refined, and some of the surprise dissipates. A portion of the original gap was indeed due to measurement uncertainties that were resolved with better data, but not all of the gap closed. After the measurements were refined, a real discrepancy remained. There were genuinely more massive galaxies, genuinely brighter galaxies, genuinely earlier than lambda CDM with standard galaxy formation predicted. The gap was smaller than the initial dramatic claim suggested, but it was not zero. The early universe really did form galaxies faster and more abundantly than the standard predictions. This residual gap is the real scientific puzzle, the part that survived careful scrutiny. The next question is what the residual gap means. There are broadly two kinds of explanation. The first is that the gap reflects a problem with galaxy formation theory, the relatively detailed and uncertain theory of how gas turns into stars within dark matter halos. If star formation in the early universe was more efficient than the standard galaxy formation models assumed, the gap could be explained without changing the fundamental cosmology. This is the more conservative explanation, and it is favoured by many researchers because it does not require overturning the well-established lambda CDM model. The second kind of explanation is that the gap reflects a problem with the fundamental cosmology itself. If lambda CDM is wrong in some way, if the universe expanded differently or contained different amounts of matter, or had different initial conditions than the model assumes, then the predictions for early galaxies would be different, and the gap might be explained by a revised cosmology. This is the more radical explanation, and it is favoured by fewer researchers. because it requires changing a model that has been extraordinarily successful in many other domains. Distinguishing between these two kinds of explanation is the central challenge. Both can, in principle, account for the observed gap. The question is which one is correct, or whether both play a role. Resolving this requires careful analysis of the observations, comparison with detailed models, and additional data from continued observations. It is not a question that can be settled quickly or easily. It is the kind of question that may take years or decades of work to resolve fully. The current consensus, insofar as there is one, leans toward the more conservative explanation that the gap primarily reflects more efficient star formation in the early universe, a problem with galaxy formation theory rather than with fundamental cosmology. The evidence for this is that the observed galaxies, on careful analysis, do not clearly exceed what lambda CDM can provide. They require high but not impossible star formation efficiencies. This suggests that the cosmology is intact and that the galaxy formation theory needs revision. But this consensus is provisional, and a significant minority of researchers continue to explore the possibility that the observations point to deeper problems. The gap, then, is real but interpretable in more than one way. It clearly indicates that our understanding clearly demands revision of some part of our theories. But whether the revision is confined to the details of galaxy formation or extends to the fundamental cosmology remains genuinely uncertain. This uncertainty is not a sign of confusion or failure. It is the normal state of an active scientific question. In the period after a surprising discovery and before a settled explanation, the gap is being studied, the explanation is being sought, the answer is not yet known. The dramatic phrasing that the James Webb Space Telescope broke cosmology makes for compelling headlines, but it deserves careful scrutiny. Did the telescope actually break cosmology? The honest answer, based on the current state of the evidence, is probably not, at least not the fundamental cosmological model. But the question is more interesting than a simple yes or no, and the nuances are worth exploring. First, what would it mean to break cosmology? It would mean that the observations could not be reconciled with the standard model lambda CDM, no matter how the details were adjusted. It would mean that the model made a prediction that the observations definitively contradicted in a way that could not be explained by refining the less fundamental parts of the theory. This is a high bar. Scientific models are not broken by every surprising observation. They are broken only when the contradiction is fundamental and irreconcilable. By this standard, the James Webb observations have not broken cosmology. The surprising galaxies, on careful analysis, can be reconciled with lambda CDM by adjusting the theories of galaxy formation, specifically by allowing for more efficient star formation in the early universe. This adjustment is significant, but it does not require overturning the fundamental model. The cosmology, the expansion history, the matter content, the growth of structure remains intact. What needs revision is the more detailed and uncertain theory of how galaxies form within that cosmology. This is an important distinction, and it is often lost in popular accounts. The fundamental cosmological model and the theory of galaxy formation are different things, with different levels of establishment. Lambda CDM, the fundamental model, is supported by many independent lines of evidence and has passed many stringent tests. Galaxy formation theory, by contrast, is known to be incomplete and approximate, involving complicated physics that is difficult to model. A surprise in galaxy formation does not threaten the fundamental cosmology. It threatens only the detailed theory of how galaxies form, which was never as solid as the cosmology itself. So in the most precise sense, the telescope did not break cosmology. It revealed that our theories of galaxy formation are incomplete, that the early universe formed galaxies more efficiently than we assumed. This is a significant finding requiring real revision of our understanding. But it is a revision of the details, not a revolution in the fundamentals. The headline, "James Webb Breaks Cosmology," overstates the case, at least as the evidence currently stands. That said, the situation is not entirely settled, and it would be wrong to dismiss the possibility of deeper problems. A minority of researchers have argued that the observations might point to issues with the fundamental cosmology after all. There are proposals that invoke modified cosmological models, different forms of dark energy, different expansion histories, different initial conditions, to explain the early galaxies. These proposals are speculative, and most cosmologists do not currently favour them, but they are not ruled out. The possibility that the telescope has revealed a deeper problem, while not the leading explanation, remains open. Moreover, the James Webb observations connect to another independent puzzle in cosmology, the Hubble tension, a long-standing disagreement about how fast the universe is expanding. Some of the proposals to explain the early galaxies also bear on the Hubble tension, suggesting that the two puzzles might have a common solution involving new physics. If this turns out to be the case, then the James Webb observations might, after all, be pointing toward a genuine problem with the fundamental cosmology, one that was already hinted at by the Hubble tension. This connection is intriguing and is a subject of active research. So the most accurate answer to "did James Webb break cosmology?" is nuanced. The telescope did not break the fundamental cosmological model, as far as the current evidence shows. It revealed a real problem with our theories of galaxy formation, which need revision to accommodate the rapid formation of early galaxies. This is significant but not revolutionary. However, the possibility of deeper problems is not entirely ruled out, and the connection to the Hubble tension keeps alive the prospect that something more fundamental might be going on. The question is not fully settled, and it remains an active area of investigation. What is certain is that the telescope revealed something genuinely surprising and genuinely important about the early universe. Whether it broke cosmology or merely challenged our understanding of galaxy formation, it changed what we know. It demonstrated that the early universe was more active, more productive, and more surprising than we had thought. That regardless of the ultimate resolution, is a major scientific contribution. The telescope did its job. It showed us the early universe, and the early universe turned out to be more interesting than we expected. The surprising galaxies were not the only puzzle the James Webb Space Telescope revealed about the early universe. The telescope also found supermassive black holes that appeared too early and too large to be easily explained. These early black holes pose their own version of the too big, too soon problem, and they add another layer to the puzzle of how the early universe assembled its structures so quickly. Supermassive black holes are found at the center of most large galaxies. They contain millions to billions of times the mass of the Sun, concentrated in a region from which not even light can escape. The black hole at the center of the Milky Way contains about 4 million solar masses. The black holes at the centers of larger galaxies can contain billions of solar masses. How these enormous black holes formed, and how they grew so large, is a long-standing question in astrophysics. The standard picture is that supermassive black holes grow over time by accreting matter, pulling in gas and stars from their surroundings, and by merging with other black holes. Starting from a smaller seed black hole, the black hole grows gradually, over hundreds of millions or billions of years, as it consumes matter and merges with others. This gradual growth, like the gradual assembly of galaxies, takes time. The largest black holes should appear only after enough time has passed for the growth to occur. The James Webb Space Telescope, however, found supermassive black holes in the early universe that were surprisingly large for their epoch. Black holes containing millions or even billions of solar masses were found at times only a few 100 million years after the Big Bang, too early, according to the standard picture, for them to have grown so large. Like the surprising galaxies, the early black holes appeared to have assembled their mass faster than the standard models allowed. The problem is one of growth rate. There is a limit to how fast a black hole can grow by accretion, called the Eddington limit. As matter falls into a black hole, it heats up and radiates, and the radiation pushes back against the infalling matter. At a certain rate of accretion, the outward push of the radiation balances the inward pull of gravity, and faster accretion becomes difficult. This sets a maximum rate at which a black hole can grow. Starting from a typical seed black hole and growing at the maximum rate, it takes a certain amount of time to reach a given mass. For the largest early black holes, the time required, growing from a typical seed, exceeds the age of the universe at the epoch they are observed. This means that either the early black holes started from larger seeds, or they grew faster than the standard limit allows, or some other explanation applies. Several possibilities have been proposed. One is that the seed black holes were unusually large, formed not from the collapse of individual stars as typical seeds are thought to be, but from the direct collapse of large clouds of gas, producing seeds of tens of thousands of solar masses or more. Starting from such large seeds, the black holes would have a head start and could reach large masses more quickly. Another possibility is that the early black holes grew faster than the Eddington limit, through episodes of super-Eddington accretion. Under certain conditions, matter might fall into a black hole faster than the standard limit allows, at least for short periods. If the early black holes underwent episodes of super-Eddington accretion, they could have grown faster than the standard picture predicts, reaching large masses in the limited time available. The early black holes connect to the early galaxies in an interesting way. The growth of black holes and the formation of stars are linked, both depend on the availability of gas, and both are influenced by the conditions in the early universe. The same factors that allowed rapid star formation in the early galaxies might also have allowed rapid black hole growth. The puzzles of early galaxies and early black holes may share a common root in the conditions of the early universe, which favoured rapid assembly of structure in ways the standard models did not fully anticipate. The early black holes, like the early galaxies, thus add to the picture of an early universe that built its structures faster than expected. They are another manifestation of the same broad surprise. The early universe was more efficient, more rapid, more productive than the standard theories assumed. Whether this requires new physics or merely a better understanding of the conditions in the early universe is, as with the galaxies, an open question. The early black holes are a significant piece of the puzzle, and they reinforce the sense that something about the early universe was different from what we had thought. Among the most puzzling discoveries of the James Webb Space Telescope is a class of objects that came to be called little red dots. These are compact, red objects found in the early universe, with properties that do not fit neatly into any established category. They are among the strangest things the telescope has found, and understanding them has become one of the active frontiers of early universe research. The little red dots are, as the name suggests, small and red in the telescope's images. They are compact, much smaller in apparent size than typical galaxies, and they have a distinctive red colour, indicating that their light is concentrated toward longer wavelengths. They appear in significant numbers in the early universe, at redshifts corresponding to the first billion years or so after the Big Bang. They were not predicted by any prior theory, and their nature was initially mysterious. As astronomers studied the little red dots in more detail, a puzzle emerged. The objects seem to have characteristics of both galaxies dominated by stars and galaxies dominated by accreting black holes, but they did not fit cleanly into either category. Their spectra showed features that suggested the presence of a growing supermassive black hole, a so-called active galactic nucleus, but other features suggested the presence of a substantial population of stars. The objects seemed to be some kind of hybrid, or perhaps a type of object in a phase of evolution not previously observed. One interpretation is that the little red dots are early galaxies in which a supermassive black hole is growing rapidly, surrounded by dense gas and stars. The black hole's accretion produces some of the light, while stars produce the rest. The compact size and red colour result from the dense, dusty environment surrounding the growing black hole. In this interpretation, the little red dots represent an early phase in the coevolution of galaxies and their central black holes, a phase in which both are growing rapidly in a dense, compact environment. Another interpretation emphasizes the stellar component, suggesting that the little red dots are extremely dense concentrations of stars, with the red color resulting from dust or from the properties of the stellar population. In this view, the black hole may play a smaller role, and the objects are primarily very compact, very dense early galaxies. The debate between these interpretations, and others, is ongoing. The little red dots have not been definitively characterized, and their nature remains a subject of active research. What makes the little red dots particularly interesting is that they are numerous. They are not a handful of rare oddities. They appear in significant numbers in the early universe, suggesting that they represent a common type of object or a common phase of evolution at early times. Whatever they are, they were a significant component of the early universe, common enough that any complete picture of early cosmic history must account for them. Their abundance makes them important, regardless of their exact nature. The little red dots also seem to become rare at later epochs. They are common in the early universe but largely absent in the present universe. This suggests that they are a transient phenomenon, a phase that early structures pass through, but that does not persist to the present day. If the little red dots are an early phase in the growth of galaxies and their black holes, then understanding them could illuminate how galaxies and black holes grew in the early universe and evolved into the structures we see today. The discovery of the little red dots illustrates a broader point about the James Webb Space Telescope's impact. The telescope did not merely confirm or refute existing predictions, it revealed entirely new classes of objects that no one had anticipated. The little red dots were not predicted by any theory. They emerged from the data as a genuine surprise, a new kind of object demanding explanation. This is one of the most valuable things a powerful new instrument can do, not just test existing ideas, but reveal phenomena that no one had imagined, opening new questions and new directions for research. The little red dots remain at present among the strangest and least understood objects in the early universe. They are a reminder that the early universe held surprises beyond the massive galaxies and early black holes, that it was populated with objects and phenomena that our theories had not foreseen. As astronomers continue to study them, the little red dots may reveal new aspects of how the early universe assembled its structures. For now, they stand as one of the telescope's most intriguing and unexpected discoveries, a puzzle still very much in the process of being solved. Few objects better illustrate how much the early universe still has to teach us. The puzzles raised by the James Webb Space Telescope did not arise in a vacuum. Cosmology was already grappling with another independent puzzle, one that had been building for years before the telescope launched. This puzzle is called the Hubble tension, and it concerns a fundamental disagreement about how fast the universe is expanding. Understanding the Hubble tension is important because it represents a possible pre-existing crack in the Standard Model, and because some proposed solutions to it connect to the James Webb findings. The expansion of the universe is described by a number called the Hubble constant, which measures how fast the universe is expanding at the present time. It tells you how quickly a galaxy at a given distance is receding from us due to cosmic expansion. The Hubble constant is one of the most important numbers in cosmology because it sets the scale for the size and age of the universe. Measuring it accurately has been a central goal of cosmology for decades. The Hubble tension arises because there are two main ways to measure the Hubble constant, and they give different answers. The two methods are independent, based on different physics and different observations. If the standard cosmological model were complete and correct, the two methods should give the same answer. But they do not. They disagree by an amount that is too large to be explained by measurement errors alone. This disagreement is the Hubble tension. The disagreement has a particular character that makes it especially troubling. It is not that one measurement is precise and the other is sloppy. Both measurements are highly precise, the results of decades of careful work by large teams of researchers. Both have small, well-characterized uncertainties. The problem is that the two precise values simply do not match. They sit apart from each other, each with small error bars with a clear gap between them. This is the worst kind of disagreement to have, because it cannot be dismissed as the result of a single imprecise measurement. Two careful methods, applied to the same universe, return two different answers. The first method measures the Hubble constant from the local universe, using relatively nearby objects. Astronomers use a distance ladder, a series of overlapping techniques for measuring distances to progressively more distant objects. They start with nearby stars whose distances can be measured directly, then use those to calibrate brighter objects that can be seen farther away, and so on, building up a ladder of distance measurements that reaches out to distant galaxies. Combined with the measured recession velocities of those galaxies, this gives a measurement of the Hubble constant. This local method yields a relatively high value for the Hubble constant. The second method measures the Hubble constant from the early universe using the cosmic microwave background, the ancient light from 380,000 years after the Big Bang. The patterns in this ancient light encode information about the early universe, and by combining this information with the standard cosmological model, astronomers can infer the Hubble constant. This early universe method yields a relatively low value for the Hubble constant, lower than the local method by about 9%. A 9% difference might not sound like much, but in this context it is highly significant. Both methods have been refined over many years, and their uncertainties have been reduced to the point where a 9% disagreement is far larger than the combined uncertainties. The two methods are not consistent with each other. One of them is wrong, or the standard model that connects them is wrong, or there is some unknown systematic error in one or both. The disagreement has persisted and even strengthened as the measurements have improved, which makes it harder to dismiss as a mere error. The Hubble tension has been one of the central puzzles in cosmology for the past several years. It suggests to some researchers that the standard model might be incomplete, that there might be some new physics not captured by lambda CDM that affects the expansion of the universe. Various proposals have been put forward to explain the tension, many of them involving modifications to the standard model. None has been definitively established, and the tension remains unresolved. It is a real, persistent disagreement that the standard model in its current form cannot fully explain. The significance of the Hubble tension in the context of the James Webb findings is that it represents a possible pre-existing problem with the standard cosmology, a crack that was already there before the telescope launched. If the standard model is incomplete in some way that affects the expansion of the universe, that incompleteness might also affect the predictions for early galaxy formation. The James Webb puzzle and the Hubble tension might be connected, two symptoms of the same underlying problem with the standard model. This possibility, explored in the next sections, is one of the most intriguing aspects of the current situation in cosmology. The two methods of measuring the Hubble constant deserve a closer look, because the nature of their disagreement is central to understanding what the Hubble tension might mean. The two methods approach the question from opposite ends of cosmic history, one from the present, one from the distant past, and the fact that they disagree carries deep implications. The local method, sometimes called the late universe or distance ladder method, measures the expansion rate using objects in the relatively nearby universe. The foundation of this method is the direct measurement of distances to nearby objects. For the nearest stars, distances can be measured by parallax, the apparent shift in a star's position as the Earth orbits the Sun, which depends on the star's distance. Parallax provides a direct geometric measurement of distance, independent of any assumptions about the star's brightness. From this foundation, astronomers build the distance ladder. They use the nearby stars, whose distances are known from parallax, to calibrate a class of variable stars called Cepheids, whose brightness varies in a regular way related to their intrinsic luminosity. Once calibrated, Cepheids can be used to measure distances to galaxies far enough away to contain them. Within those galaxies, astronomers calibrate an even brighter class of objects, a particular type of supernova, that can be seen at much greater distances. Using these supernovae, they measure distances to far-off galaxies, and combined with the recession velocities of those galaxies, they determine the Hubble constant. Each rung of the ladder builds on the one before, extending the distance measurements outward. The early universe method, by contrast, does not use a distance ladder. It uses the cosmic microwave background, the ancient light from the early universe. The patterns in this light, the subtle variations in temperature across the sky, were imprinted by physical processes in the early universe, and they encode the values of the cosmological parameters, including the Hubble constant. By measuring these patterns precisely and fitting them with the standard cosmological model, astronomers infer the value of the Hubble constant that the early universe implies. This method depends on the standard model to connect the early universe observations to the present-day expansion rate. The two methods are thus fundamentally different. The local method is direct and largely model-independent, building up distances step by step from geometric foundations. The early universe method is indirect and model-dependent, inferring the expansion rate from ancient light through the lens of the standard cosmological model. The local method looks at the universe as it is now. The early universe method looks at the universe as it was and extrapolates forward using the model. When the two methods agree, it is a powerful confirmation of the standard model. It means that the model correctly connects the early universe to the present. For many years, the two methods did agree within their uncertainties, and this agreement was taken as evidence that the standard model was working well. The Hubble constant seemed to have a consistent value, measured the same way from both ends of cosmic history. This consistency was reassuring. But as the measurements improved, the agreement broke down. The local method consistently gave a higher value than the early universe method, and the gap between them grew more significant as the uncertainties shrank. The two methods, measured ever more precisely, refused to converge. They settled on different values, separated by about 9%, with uncertainties small enough that the difference could not be dismissed. This is the Hubble tension in its current form. Two precise, independent measurements that disagree. The disagreement could mean several things. It could mean that one of the methods has an undiscovered systematic error, some subtle bias that shifts its result. A great deal of effort has gone into searching for such errors, and none has been found that can explain the full discrepancy, though the possibility cannot be entirely excluded. Alternatively, The disagreement could mean that the standard model, which connects the early universe to the present, is incomplete, that some new physics, not captured by the model, causes the expansion rate to differ from what the model predicts. This is the more profound possibility, and it is the one that connects the Hubble tension to the broader question of whether the standard cosmology is complete. If the standard model is incomplete in a way that affects the expansion history, then it might also affect the predictions for early galaxy formation, which brings us back to the James Webb puzzle. The two puzzles, approached from different directions, might be pointing to the same underlying issue. This is the connection that has made some researchers wonder whether the James Webb observations and the Hubble tension are two faces of a single deeper problem with our understanding of the universe. There is something philosophically striking about the Hubble tension. Two careful independent measurements of the same quantity, the expansion rate of the universe, refuse to agree. Each measurement has been checked and rechecked, refined and re-refined, by many researchers using many techniques. Each is believed to be reliable, and yet they disagree persistently by an amount that cannot be explained away. The numbers refuse to agree, and that refusal is telling us something. In science, when two reliable measurements of the same quantity disagree, it is a signal that something is being misunderstood. Either one of the measurements has a hidden error, or the theoretical framework connecting them is flawed. The disagreement is not a failure of science. It is science working as it should. The persistence of the disagreement despite intense scrutiny is what makes it scientifically valuable. It is pointing towards something we do not yet understand. The history of science contains many examples of such disagreements leading to major discoveries. A small, persistent discrepancy in the orbit of the planet Mercury, which Newtonian gravity could not explain, eventually pointed the way to Einstein's general theory of relativity. A puzzling constancy in the measured speed of light regardless of the observer's motion led to the theory of special relativity. Small stubborn disagreements between measurement and theory have repeatedly been the seeds of scientific revolutions. The Hubble tension might be such a seed, or it might turn out to be a mundane measurement error. Which it is remains to be seen. The researchers who measure the Hubble constant by the local method have examined their techniques exhaustively, searching for any error that could explain the discrepancy. They have checked their calibrations, their assumptions, their instruments. They have used different types of objects and different versions of the distance ladder. The high value they measure has held up under all this scrutiny. Similarly, the researchers who measure the Hubble constant from the cosmic microwave background have examined their analysis thoroughly, and the low value they infer has also held up. Neither side has found an error that resolves the tension. This mutual robustness is what makes the tension so interesting. If one method were clearly less reliable than the other, the disagreement could be attributed to the weaker method. But both methods are highly developed and carefully checked. Both are believed to be reliable by the experts who use them. The disagreement is between two strong measurements, not between a strong one and a weak one. This is precisely the situation that suggests a problem with the underlying theory rather than with the measurements themselves. If the problem is with the underlying theory, if the standard model is incomplete in some way, then resolving the Hubble tension would require new physics. Various proposals have been advanced. Some involve a new form of energy in the early universe, sometimes called early dark energy, that would change the early expansion history and reconcile the two measurements. Others involve modifications to the properties of dark matter, or to the nature of dark energy, or to the fundamental laws governing the expansion. None of these proposals has been confirmed, and each has its own difficulties, but they represent serious attempts to explain the tension through new physics. The connection to the James Webb findings comes through these proposals. Some of the same modifications to the standard model that might resolve the Hubble tension would also change the predictions for early galaxy formation. Early dark energy, for instance, would alter the early expansion history in a way that could allow galaxies to form earlier and grow faster, potentially explaining the surprising James Webb galaxies. If a single modification to the standard model could resolve both the Hubble tension and the James Webb puzzle, that would be a strong argument in its favour. The possibility of such a unified solution is one of the most actively explored ideas in current cosmology. This is where the two puzzles converge. The Hubble tension, a disagreement about the present expansion rate, and the James Webb puzzle, a surprise about early galaxy formation, might both be symptoms of the same underlying incompleteness in the standard model. If so, then the numbers that refuse to agree, The two measurements of the Hubble constant and the galaxies that form too fast might be telling the same story, that our understanding of the universe, successful as it is missing something. What that something is, no one yet knows, but the convergence of the two puzzles has made the search for it more urgent and more focused. It is also possible, of course, that the convergence is a coincidence, that the two puzzles have separate explanations and merely happen to be unresolved at the same time. Science has seen apparent connections dissolve under scrutiny before, but the possibility of a common cause is too tempting and too potentially important to ignore. It's being pursued vigorously even as the more conservative explanations are also explored. When faced with puzzles like the Hubble tension and the surprising early galaxies, cosmologists do what scientists always do. They propose explanations and test them against the data. A number of proposals have emerged, ranging from conservative adjustments to radical new physics. Examining these proposals reveals the range of possibilities under consideration and the difficulty of finding a solution that explains everything. The most discussed proposal is early dark energy. The idea is that in addition to the dark energy that drives the accelerating expansion of the present universe, there might have been an additional component of dark energy active in the early universe, which then faded away. This early dark energy would have altered the expansion history of the early universe, changing the relationship between the early universe and late universe measurements of the Hubble constant. If tuned appropriately, early dark energy could reconcile the two measurements, resolving the Hubble tension. Early dark energy has the appealing feature that it might also help with the James Webb puzzle. By changing the early expansion history, early dark energy would change the timeline of structure formation, potentially allowing galaxies to form earlier and grow faster. Some studies have found that early dark energy models can produce more massive galaxies at early times than the standard model, bringing the predictions closer to the James Webb observations. This dual benefit, resolving the Hubble tension and easing the James Webb puzzle, is what makes early dark energy an attractive proposal to its proponents. But early dark energy is not without problems. It requires introducing a new component of the universe, with specific properties tuned to resolve the tension, and there is no independent evidence for its existence. It also faces challenges from other cosmological data, which constrain how much early dark energy could have been present. The proposal is taken seriously and actively studied, but it is far from established. It is one possibility among several with its own strengths and weaknesses. Other proposals to resolve the Hubble tension involve different kinds of new physics. Some involve changes to the properties of neutrinos, the nearly massless particles that pervade the universe. Some involve interactions between dark matter and dark energy, or between dark matter and ordinary matter, that are not present in the standard model. Some involve modifications to the law of gravity itself on cosmological scales. Each of these proposals attempts to explain the Hubble tension through some departure from the standard model, and each has been explored in the cosmological literature. For the James Webb puzzle specifically, the proposed fixes fall into two broad categories, corresponding to the two kinds of explanation we have discussed. The first category accepts the standard cosmology and modifies the theory of galaxy formation, allowing for more efficient star formation, a different population of early stars, weaker feedback, or other adjustments to how galaxies form. This is the conservative approach, and it is favoured by most researchers. The second category modifies the fundamental cosmology through early dark energy or other new physics to change the timeline of structure formation. This is the more radical approach, favoured by fewer researchers but still actively explored. The challenge is that the data do not yet clearly favour one approach over another. The conservative approach, modifying galaxy formation theory, can explain the James Webb observations without new fundamental physics, and it is preferred on grounds of conservatism. But it does not address the Hubble tension, which remains a separate puzzle. The radical approach, modifying the fundamental cosmology, could potentially address both puzzles at once, which is appealing, but it requires new physics for which there is no independent evidence. Neither approach is clearly correct, and the choice between them is not yet determined by the data. This is the current state of the field, a range of proposals, none confirmed, each with strengths and weaknesses. The conservative proposals can explain the galaxies but not the Hubble tension. The radical proposals might explain both but require unproven new physics. The data are not yet decisive. Resolving the situation will require more observations, more theoretical work, and more time. The proposals are being tested against each new piece of data, and gradually the range of viable possibilities is being narrowed. But a definitive answer has not yet emerged. What this proliferation of proposals reflects is a field in a state of productive uncertainty. The puzzles are real, the stakes are high, and the possible explanations are numerous. This is not a sign of crisis, but of vitality. The puzzles have stimulated a wave of theoretical creativity and observational effort. Out of this effort, eventually, a clearer picture will emerge. For now, the proposed fixes remain proposals, possibilities under investigation, awaiting the data that will confirm or refute them. The universe is keeping its secrets for the moment, while the scientists work to uncover them. Before accepting that the universe requires new physics, it is worth taking seriously the most mundane possibility, that the measurements are simply wrong. Astronomical measurements of the distant universe are difficult, and there are many ways for errors to creep in. Perhaps the surprising galaxies are not as massive or as early as they appear. Perhaps that the Hubble tension is an artifact of some undiscovered systematic error. The possibility that our measurements are misleading us must be considered carefully before more exotic explanations are embraced. Consider the mass estimates for the early galaxies. To estimate the mass of stars in a distant galaxy, astronomers measure its brightness and colour, then use models of stellar populations to infer how many stars of various types must be present to produce that light. This inference depends on assumptions about the distribution of stellar masses, the ages of the stars, the amount of dust, and other factors. If these assumptions are wrong, the mass estimates could be off, potentially by a large factor. A galaxy that appears very massive might actually contain fewer stars than estimated, if the assumptions about its stellar population are incorrect. One particular assumption that has received attention is the distribution of stellar masses, called the initial mass function. This describes how many stars of each mass form when a population of stars is created. The standard assumption is based on observations of star formation in the nearby universe. But if the initial mass function was different in the early universe, if early star formation produced relatively more massive luminous stars, then a given amount of light would correspond to fewer total stars, and the mass estimates would be lower. A different initial mass function in the early universe could reduce the inferred masses of the early galaxies, easing the tension with the standard model. There is some physical motivation for thinking the early initial mass function might have been different. The first stars formed from pristine gas, lacking heavy elements, and such gas may preferentially form more massive stars. If the early galaxies contained relatively more massive stars than nearby galaxies, their light would overestimate their total stellar mass under standard assumptions. Correcting for this could bring the mass estimates down, reducing or eliminating the apparent excess. This is an active area of investigation, and it represents a way the tension might be resolved without new fundamental physics, and even without dramatic changes to galaxy formation efficiency. The brightness of the early galaxies, rather than their inferred mass, might also be misleading in other ways. Some of the light attributed to stars might actually come from accreting black holes, which can be very luminous. If a significant fraction of an early galaxy's light comes from a central black hole rather than from stars, then the stellar mass inferred from that light would be overestimated. The little red dots, discussed earlier, illustrate this ambiguity. Objects whose light might come from stars, from black holes, or from both. Disentangling these contributions is difficult and could affect the mass estimates. For the Hubble tension, the possibility of systematic error has been examined exhaustively. Both the local and early universe methods have been scrutinized for hidden biases. In the local method, attention has focused on the calibration of the distance ladder, whether the Cepheids or supernovae might be systematically mismeasured in some way. In the early universe method, attention has focused on the analysis of the cosmic microwave background and the assumptions of the standard model used to interpret it. Despite this scrutiny, no error has been found that resolves the tension. But the possibility of some subtle, undiscovered systematic error cannot be entirely excluded. The careful consideration of measurement errors is an essential part of the scientific process. It would be premature to conclude that the universe requires new physics if the puzzles could be explained by mundane errors in the measurements. This is why so much effort goes into checking the measurements, refining the analysis, and testing the assumptions. Only when the measurements have been thoroughly verified and the puzzles persist does it become reasonable to consider more radical explanations. The field is still in the process of this verification, and the question of whether the measurements are reliable is not fully settled. At the same time, the puzzles have persisted through considerable scrutiny. The surprising galaxies have been confirmed spectroscopically, and while their masses remain uncertain, the basic finding of rapid early galaxy formation has held up. The Hubble tension has survived years of checking and has even strengthened. It is becoming progressively harder to attribute the puzzles entirely to measurement errors. This does not prove that new physics is required. The conservative explanations involving galaxy formation remain viable, but it does suggest that the puzzles are pointing to something real, whether in our astrophysics or in our cosmology. The measurements might be wrong in some details, but they are probably not entirely wrong. Something genuine is being revealed. Among the more radical ideas floated in response to the James Webb findings is the possibility that the universe is older than the Standard Model says. If the universe were older, if more time had elapsed since the Big Bang than the standard 13.8 billion years, then there would have been more time for early galaxies to form, easing the too soon part of the puzzle. This idea is not widely accepted, but it is worth examining, both for what it proposes and for why most cosmologists do not embrace it. The age of the universe, in the Standard Model, is derived from the cosmological parameters, including the Hubble constant and the matter content. Given these parameters, the model calculates how long the universe has been expanding, arriving at the figure of approximately 13.8 billion years. This age is consistent with other measurements, such as the ages of the oldest stars and the oldest globular clusters, which are slightly less than 13.8 billion years, as they should be since they formed after the Big Bang but early in cosmic history. The standard age fits together with these independent constraints. The proposal that the universe is older would require revising the cosmological parameters or the model itself. Some specific proposals have suggested ages substantially greater than 13.8 billion years, in some cases nearly twice as large. These proposals typically involve unconventional cosmological models, with different assumptions about the expansion history or the nature of the cosmic constituents. If the universe were, say, 27 billion years old, there would be ample time for early galaxies to form, and the James Webb puzzle would dissolve. But these proposals face serious difficulties. The standard age of 13.8 billion years is not an isolated number. It is woven into the entire fabric of the Standard Model, consistent with a vast array of observations. Changing the age would require changing many other things, and those changes would generally conflict with other well-established measurements. The cosmic microwave background, the abundances of the light elements, the large-scale structure of the universe, all of these are consistent with the standard age. A radically older universe would struggle to remain consistent with all of these constraints simultaneously. The ages of the oldest stars provide a particular constraint. Astronomers can estimate the ages of the oldest stars in our galaxy, and these ages come out to slightly less than the standard age of the universe, around 13 billion years. This is consistent with the Standard Model. The oldest stars formed early in cosmic history, a bit after the Big Bang. If the universe were much older, we would expect to find stars much older than 13 billion years, and we do not. The absence of stars older than about 13 billion years is evidence against a radically older universe. For these reasons, the proposal that the universe is much older than 13.8 billion years is not taken seriously by most cosmologists. It would solve the James Webb puzzle, but at the cost of conflicting with many other observations. The standard age is too well established, too consistent with independent measurements to be revised so dramatically. The James Webb findings, significant as they are, do not provide enough reason to overturn the well-supported age of the universe. This illustrates an important principle in evaluating proposed solutions to scientific puzzles. A solution must not only explain the puzzle in question, it must also remain consistent with everything else we know. A proposal that solves one puzzle but creates conflicts with many other observations is not a good solution. The standard age of the universe is supported by so many independent lines of evidence that any proposal to change it must overcome an enormous weight of contrary evidence. The James Webb puzzle, by itself, does not come close to providing that. The age proposal does, however, serve a useful purpose in the scientific conversation. By being put forward and examined, it clarifies what the constraints actually are and why the standard age is so robust. Even proposals that are ultimately rejected contribute to understanding by forcing a careful articulation of the evidence. The proposal that the universe is older than we think is most likely wrong. But considering it helps to clarify why the standard age is trusted, and why the James Webb puzzle must be solved in some other way, most likely through a better understanding of how galaxies formed, rather than through a revision of the fundamental timeline of cosmic history. There is a broader lesson here about how cosmology handles surprising data. The temptation when faced with an anomaly is to reach for the most dramatic possible explanation, to declare that everything must be rethought, that the foundations are crumbling. But the discipline of science requires the opposite instinct, to ask which explanations are consistent with everything else we know, and to prefer the least disruptive one that fits the data. The age of the universe is so thoroughly constrained that revising it would be the most disruptive possible move. That is so precisely why it is the wrong move, and why the search for answers leads elsewhere. If the fundamental cosmology is probably intact, and the universe is probably not older than we think, then the most likely resolution of the James Webb puzzle lies in revising our understanding of how galaxies form. This is the conservative explanation, favoured by most researchers, that the early universe formed galaxies more efficiently than our theories assumed, for reasons rooted in the different conditions of the early cosmos. Rewriting the recipe for galaxy formation, rather than overturning cosmology, is the path most researchers expect to lead to a solution. The theory of galaxy formation describes how gas, falling into dark matter halos, turns into stars. It is a complicated theory, involving many physical processes operating across a vast range of scales. Gas must cool and collect into dense clouds. The clouds must collapse to form stars. The stars produce radiation, and when they die, explosions that heat and disperse the surrounding gas. This feedback regulates further star formation. Black holes form and grow, producing their own feedback. The interplay of all these processes determines how efficiently a galaxy converts its gas into stars. Modelling this interplay accurately is extremely difficult. Because the theory is so complicated and involves so many uncertain processes, it is not surprising that it might be wrong in some respects. The standard galaxy formation models were calibrated largely against observations of the nearby universe, where conditions are different from those in the early universe. Extrapolating these models to the early universe, with its higher densities and different conditions, was always uncertain. The James Webb observations suggest that this extrapolation was not entirely correct, that early galaxy formation proceeded differently than the nearby calibrated models predicted. The specific revision suggested by the observations is that early star formation was more efficient, that a larger fraction of the available gas converted into stars than the standard models assumed. We have discussed several reasons why this might be the case. The higher density of the early universe, a different population of first-generation stars, weaker feedback. Any or all of these factors could have made early star formation more efficient, allowing early galaxies to grow faster and become more massive than the standard models predicted. Incorporating these factors into the models is the work of rewriting the recipe. This work is well underway. Researchers are developing new models of galaxy formation that account for the conditions of the early universe and that aim to reproduce the James Webb observations. These models explore higher star formation efficiencies, different stellar populations, and modified feedback. Some of them succeed in producing more massive early galaxies closer to what the telescope observed. The models are being tested against the growing body of observations, and gradually they are being refined to match the data. This is normal scientific progress. The theory is being adjusted to account for new observations. The revision of galaxy formation theory is significant, but it is not a crisis. Galaxy formation theory was always known to be incomplete and approximate. Revising it in the light of new observations is exactly what should happen. The James Webb observations have provided crucial new data about galaxy formation at the earliest epochs, and that data is being used to improve the theory. This is the telescope doing its job, revealing the early universe in unprecedented detail and forcing our theories to improve to match what is seen. It is worth emphasizing that this conservative resolution, if it holds, would still represent a major scientific advance. Understanding how galaxies formed in the early universe, why star formation was so efficient, what the first stars were like, how feedback operated, is a profound question. The James Webb observations are driving progress on this question, forcing a deeper understanding of the processes that built the first galaxies. Even if the fundamental cosmology is untouched, The revision of galaxy formation theory is a substantial contribution to our understanding of cosmic history. The recipe for galaxy formation, then, is being rewritten. The new recipe will include more efficient early star formation, and probably other revisions as well, to account for what the telescope has seen. This rewriting is the most likely resolution of the James Webb puzzle, not a revolution in cosmology, but a substantial improvement in our understanding of how galaxies form. It is less dramatic than breaking cosmology, but it is real progress, driven by real observations toward a better understanding of the early universe. The telescope has shown us that our recipe was incomplete. Now the work is to make it complete. There is a certain satisfaction in this kind of progress, even if it lacks the drama of a toppled theory. A puzzle was posed by the observations, and a plausible answer is emerging from careful work. The early universe formed galaxies fast because the conditions favoured fast formation. Dense gas, efficient cooling, perhaps a different first generation of stars. This is not magic, and it is not new physics. It is astrophysics operating under conditions different from those we are used to, producing results that surprised us only because our models were calibrated on a different era of cosmic history. Dark matter plays a central role in the formation of galaxies, and any discussion of how early galaxies formed must consider its part in the story. Dark matter is the invisible substance that dominates the gravity of the universe, and it provides the scaffolding within which galaxies form. Understanding its role in the early cosmos is essential to understanding both the standard predictions and the surprising James Webb observations. Dark matter makes up about 27% of the universe, compared to about 5% for ordinary matter. It does not emit, absorb or reflect light, which is why it is called dark. It is detected only through its gravity, through the way it influences the motions of stars and galaxies, and the way it bends light passing through it. Despite being invisible, dark matter is the dominant form of matter in the universe, outweighing ordinary matter by about 5-1. In the standard picture of structure formation, dark matter forms the foundation. After the Big Bang, the universe was nearly uniform, with tiny variations in density from place to place. Dark matter, being more abundant and not subject to the pressure forces that affect ordinary gas, began to collapse under gravity first, forming concentrations called halos. These dark matter halos grew over time, merging and accreting to form larger halos. The ordinary gas then fell into the gravitational wells created by the dark matter halos, where it could cool, collapse and form stars. Galaxies formed within the dark matter halos, like cities growing within a landscape shaped by invisible hills and valleys. The growth of dark matter halos sets the pace for galaxy formation. Galaxies cannot form faster than their dark matter halos grow because the halos provide the gravitational wells that gather the gas. The rate at which halos grow is determined by the properties of dark matter and by the cosmological parameters. In the standard model, with cold dark matter, the halos grow hierarchically, small ones first, large ones later, at a rate that the model predicts precisely. This predicted rate of halo growth is the foundation for the predicted rate of galaxy formation. The James Webb puzzle, in terms of dark matter, is that galaxies formed faster than the predicted growth of dark matter halos seemed to allow. If the halos grew at the standard rate, then there were not large enough halos early enough to host the massive galaxies the telescope observed, unless star formation within the halos was extremely efficient. This is why the puzzle points either to more efficient star formation, the conservative explanation, or to a problem with the standard picture of halo growth, which would implicate the cosmology or the nature of dark matter. Some proposals to explain the early galaxies involve modifying the properties of dark matter. If dark matter were not cold, if it had different properties than the standard model assumes, then the halos might grow differently, potentially allowing earlier formation of large halos. Various alternative dark matter models have been proposed, with different properties that could change the pace of structure formation. These proposals are speculative, and the standard cold dark matter model remains favoured, but they represent one avenue of explanation for the surprising observations. The nature of dark matter remains one of the great unsolved problems in physics. We know it exists from its gravitational effects, but we do not know what it is made of. Numerous experiments have searched for dark matter particles, so far without definitive success. The possibility that the James Webb observations might reveal something about the nature of dark matter, that the early galaxies might be telling us that dark matter is not quite what we assumed, adds another dimension to the puzzle. If alternative dark matter models were needed to explain the early galaxies, that would be a profound discovery, bearing on the fundamental nature of matter itself. For now, the standard cold dark matter model remains the foundation, and most explanations of the early galaxies work within it, attributing the rapid formation to efficient star formation rather than to modified dark matter. But the possibility that dark matter is involved cannot be excluded. The early universe is a laboratory for testing the properties of dark matter, and the James Webb observations are providing new data from that laboratory. Whether that data ultimately points to modified dark matter, or merely to more efficient star formation within the standard dark matter framework, is one of the questions that continued research will address. Dark matter shaped the early universe, and understanding its role is essential to understanding how the first galaxies formed so fast. The connection between dark matter and the visible galaxies is, in this sense, intimate. We cannot see dark matter directly, yet it determined where and when galaxies could form. The luminous galaxies the telescope observes are, in effect, traces of the invisible dark matter scaffolding beneath them. To study the early galaxies is, indirectly, to study the dark matter that made them possible. The very first stars in the universe, the first generation, formed from pristine gas containing only hydrogen and helium, are central to understanding the early galaxies. These first stars, often called population 3 stars, are thought to have been quite different from the stars that formed later. Although they have not yet been directly observed, their properties may hold a key to explaining the rapid formation of early galaxies. Understanding what they might have been like is an important part of the story. The first stars formed from gas that had no heavy elements. The Big Bang produced only the lightest elements, hydrogen, helium, and traces of lithium. All the heavier elements, from carbon and oxygen to iron and beyond, were produced later, inside stars. The first generation of stars, therefore, formed from gas containing none of these heavier elements. This pristine composition affected how the gas behaved when it collapsed to form stars, and consequently affected the properties of the stars that formed. Heavy elements help a gas to cool. When gas collapses to form a star, it must shed heat. Otherwise, the rising pressure halts the collapse. Heavy elements are efficient at radiating heat away, allowing gas to cool and collapse readily. Pristine gas, lacking heavy elements, cools less efficiently. This is thought to have affected the masses of the first stars. With less efficient cooling, the gas could not fragment into small pieces as easily, and tended to form more massive stars. The first stars are therefore thought to have been more massive, on average, than later generations, possibly much more massive, up to hundreds of times the mass of the Sun. Very massive stars are very luminous and very short-lived. A star hundreds of times the mass of the Sun would shine brilliantly, producing enormous amounts of light, especially ultraviolet light. But it would also exhaust its fuel quickly, living only a few million years before dying in a spectacular explosion. The first stars, if they were as massive as theory suggests, would have been brilliant but brief, lighting up the early universe and then dying quickly, dispersing the first heavy elements into the surrounding gas. This has implications for the early galaxies. If the early galaxies contained a significant population of these massive, luminous first-generation stars, they would be brighter, for a given mass, than galaxies made of ordinary stars. This could affect the interpretation of the James Webb observations. Some of the brightness of the early galaxies might come from these unusually luminous first stars, rather than indicating an unusually large total mass. If so, the mass estimates for the early galaxies might be overestimates, and the tension with the standard model might be reduced. The first stars would also have driven the early chemical enrichment of the universe. When they died, they dispersed the heavy elements they had produced into the surrounding gas. The next generation of stars formed from this enriched gas, and so on. The presence of heavy elements, like the oxygen detected in JADES-GS-Z14-0, indicates that this process of enrichment had already begun by the time we observed these galaxies, that the first stars had already lived and died, seeding the galaxies with the products of their nuclear furnaces. The detection of heavy elements in very early galaxies is evidence that the first stars formed even earlier, in the universe's first chapters. Despite their theoretical importance, the first stars have not been directly observed. They are thought to have formed very early and to have been short-lived, so they are difficult to catch in the act. Astronomers hope that the James Webb Space Telescope and/or future instruments might detect the signatures of the first stars, perhaps in the light of the earliest galaxies, or in the explosions that mark their deaths. Finding direct evidence of the first stars would be a major discovery, confirming theoretical predictions and illuminating the very beginning of cosmic structure. The first stars represent the transition from the simple, dark universe that followed the Big Bang to the complex, luminous universe of galaxies and heavy elements. They were the first objects to light up the cosmos, the first to produce heavy elements, the first to begin the long process of cosmic evolution that eventually led to planets and life. Understanding them is understanding the beginning of everything that came after, and they may hold part of the answer to the James Webb puzzle, their unusual properties potentially helping to explain why the early galaxies appear as bright and as massive as they do. The first stars are a frontier of research, still largely theoretical, but central to the story of how the universe came to be structured. In a real sense, every later star, including our own Sun, is descended from them. The chemical composition of the early universe, and how it evolved, is an important thread in understanding the early galaxies. The universe began with only the lightest elements and gradually became enriched with heavier ones as stars formed, lived, and died. Tracing this chemical evolution and detecting its signatures in early galaxies provides crucial information about the history of star formation and the nature of the first cosmic structures. The Big Bang produced a universe composed almost entirely of hydrogen and helium in a ratio of about 3:1 by mass, with only traces of lithium and essentially nothing heavier. This was the raw material from which the first stars and galaxies formed. Every atom of carbon, nitrogen, oxygen, iron, and all the other heavier elements that exist today was produced later, inside stars through nuclear fusion, and dispersed into the universe when those stars died. The chemical enrichment of the universe is the story of how these heavier elements accumulated over cosmic time. In astronomical usage, all elements heavier than helium are called metals, a usage that differs from everyday language but is standard in the field. The metallicity of a galaxy, its content of these heavier elements, is a measure of how much chemical enrichment has occurred. A galaxy with low metallicity has undergone little enrichment. Its gas is close to the primordial composition. A galaxy with high metallicity has undergone substantial enrichment, with many generations of stars having lived and died to produce the heavier elements. Metallicity is thus a kind of clock, indicating how much stellar processing has occurred. The early galaxies observed by the James Webb Space Telescope provide a window into the chemical evolution of the early universe. By analysing the spectra of these galaxies, astronomers can measure their chemical compositions and infer how much enrichment had occurred by the epoch at which they are observed. The detection of heavy elements, like the oxygen found in JADES-GS-Z14-0, indicates that enrichment was already underway, that stars had already formed and died, seeding the galaxies with their products. This tells us about the history of star formation before the epoch we directly observe. The metallicities of the early galaxies are generally found to be lower than those of present-day galaxies, as expected. The early universe had undergone less enrichment than the present universe. But the metallicities are not zero. The early galaxies have already been enriched to some degree, indicating that star formation and stellar death had already occurred before we observed them. The degree of enrichment and the specific patterns of elements provide clues about the nature of the early star formation, about how many stars formed, what kinds of stars they were, and how they enriched their surroundings. The chemical patterns can be particularly revealing. The ratio of different elements, for instance the ratio of nitrogen to carbon or of oxygen to iron, depends on the types of stars that produce them and the timescales involved. Different kinds of stars produce different elements in different proportions. By measuring these ratios in early galaxies, astronomers can infer what kinds of stars were responsible for the enrichment. The nitrogen-rich composition of MOM-Z14, mentioned earlier, is an example of such a chemical clue, hinting at a connection to the ancient globular clusters of the Milky Way and at the specific processes of early star formation. The chemistry of the early universe also bears on the question of the first stars. The first generation of stars, formed from pristine gas, would have produced a characteristic pattern of elements when they died. If astronomers could detect this characteristic pattern in early galaxies, the signature of enrichment by the first stars, it would provide evidence about the nature of those first stars. The search for the chemical signatures of the first generation of stars is an active area of research, and the James Webb observations are contributing to it by providing detailed measurements of the chemical compositions of the earliest galaxies. The chemical evolution of the universe is, Ultimately, the story of how the raw materials for planets and life were produced, the carbon in our bodies, the oxygen we breathe, the iron in our blood, all of these elements were produced in stars and dispersed into the universe over cosmic history. The early galaxies observed by the James Webb Space Telescope are the sites where this enrichment began, the places where the first heavy elements were forged and released. Studying their chemistry is studying the origins of the material that would eventually make up everything we know, including ourselves. The infant universe, chemically simple, was already beginning the process that would lead, billions of years later, to a universe rich in the elements of life. The atoms in everything around us carry that ancient history within them. Bringing together the various threads, we can attempt to sketch how a galaxy might actually form and light up in the first 300 million years of cosmic history, how the rapid assembly that the James Webb Space Telescope revealed might actually have occurred. This sketch is necessarily tentative, since the details are still being worked out, but it integrates the leading ideas into a coherent picture of early galaxy formation. It begins with dark matter. In the early universe, dark matter halos formed and grew, providing the gravitational scaffolding for galaxy formation. Even in the first few 100 million years, some halos grew large enough to gather substantial amounts of gas. The gas, primarily hydrogen and helium from the Big Bang, fell into these halos, accumulating in their gravitational wells. The density of the early universe, higher than today because the universe was more compact, meant that gas was abundant and concentrated, providing ample raw material for star formation. As gas accumulated in the halos, it began to cool and collapse. The first stars formed from this gas, the massive, luminous first-generation stars, formed from pristine material. These first stars lit up the dark universe, producing intense radiation, especially ultraviolet light. They lived briefly and died in explosions, dispersing the first heavy elements into the surrounding gas and triggering further star formation as their explosions compressed nearby gas clouds. The first burst of star formation was underway. The key to rapid galaxy growth in this picture is high star formation efficiency. In the dense gas-rich conditions of the early universe, a large fraction of the available gas converted into stars, quickly and completely. Feedback processes that limit star formation in the present universe may have been less effective in the early universe, allowing star formation to proceed more efficiently. The result was rapid accumulation of stellar mass, a galaxy building up its stars far faster than the standard nearby calibrated models predicted. The star formation occurred in bursts. Rather than forming stars at a slow, steady rate, the early galaxies formed them in intense episodes, building up substantial stellar masses in short times. These bursts produced the high luminosities that the telescope observed, especially in the ultraviolet, which is a signature of rapid recent star formation. The bursty nature of early star formation is consistent with the observations, which frequently catch early galaxies in the act of forming stars rapidly. As successive generations of stars formed, lived, and died, the galaxy became chemically enriched. The heavy elements produced by the first stars accumulated in the gas, and subsequent generations of stars formed from this enriched material. By 300 million years after the Big Bang, a galaxy like JADES-GS-Z 14-0 had already undergone multiple generations of star formation, accumulating hundreds of millions of solar masses of stars and being enriched with heavy elements like oxygen. The galaxy had assembled rapidly and efficiently in the brief span of cosmic time available. Meanwhile, at the center of the galaxy, a supermassive black hole may have been growing. Starting from a seed, possibly a large seed formed by direct collapse of gas, the black hole accreted matter rapidly, perhaps at times exceeding the standard growth limit. The growing black hole produced its own radiation, contributing to the galaxy's luminosity, and in some cases, perhaps producing the distinctive appearance of a little red dot. The co-evolution of the galaxy and its central black hole was underway, both growing rapidly in the dense early environment. The result, by 300 million years after the Big Bang, was a galaxy, a substantial collection of stars enriched with heavy elements, possibly hosting a growing supermassive black hole, shining brightly across cosmic distances. This galaxy, forming so rapidly and so early, is what the James Webb Space Telescope detected. The light it produced, having travelled for more than 13 billion years, fell on the telescope's mirror and revealed the existence of this early, rapidly assembled structure. This sketch, integrating high star formation efficiency, massive first stars, bursty star formation, chemical enrichment, and rapid black hole growth, represents the leading picture of how early galaxies might have formed so fast. It is not yet fully established, many details remain uncertain, and alternative pictures are possible. But it shows how, in principle, a galaxy could light up in 300 million years within the standard cosmological framework through efficient and rapid astrophysical processes. The challenge for researchers is to refine this picture, test it against the growing body of observations, and determine whether it fully accounts for what the telescope has seen. The work continues, but the outline of an answer is taking shape. What is striking in this picture is how quickly the universe went from darkness to light. For its first few 100,000 years, the cosmos was an opaque fog. Then came the long dark ages, with no luminous sources at all. And then, in a relatively brief span, the first galaxies ignited, lighting up the cosmos with the glow of young stars. The transition from a dark, structureless universe to one filled with luminous galaxies happened faster than we had imagined. The James Webb Space Telescope has pushed back the boundary of what we can observe, revealing galaxies earlier in cosmic history than ever before. But there are limits to how far back any telescope can ever see, set by the physics of the universe itself. Understanding these limits puts the telescope's achievements in context and clarifies what we can and cannot hope to learn about the earliest moments of cosmic history. The most fundamental limit is set by the cosmic microwave background. For about the first 380,000 years after the Big Bang, the universe was filled with a hot, dense plasma of charged particles. Light could not travel freely through this plasma. It was constantly scattered, the way light is scattered in a fog. The universe was opaque. Only when it cooled enough for the charged particles to combine into neutral atoms did it become transparent, allowing light to travel freely. The light from this moment of transition is the cosmic microwave background, the oldest light we can ever detect. We cannot see anything from before this moment using light, because light could not travel freely before it. This means that there is an absolute limit to how far back we can observe with light. The moment the universe became transparent, about 380,000 years after the Big Bang, everything before that is hidden behind the wall of the cosmic microwave background, inaccessible to any telescope that detects light. The James Webb Space Telescope, observing galaxies a few 100 million years after the Big Bang, is observing well after this transparency limit, but it cannot see past the cosmic microwave background to the earlier universe. No light-based telescope can. There is, however, a gap between the cosmic microwave background and the earliest galaxies, a period sometimes called the Cosmic Dark Ages. During this time, the universe was transparent, but there were no stars or galaxies yet to produce light. The universe was filled with neutral hydrogen gas, gradually being pulled together by gravity but not yet forming luminous structures. This period is dark in the sense that there were no luminous sources. It is difficult to observe directly because there was little light produced during it. The Cosmic Dark Ages might eventually be observed through a different means, the radio emission from neutral hydrogen. Neutral hydrogen produces a characteristic radiation at a specific wavelength, and this radiation, redshifted by cosmic expansion, might be detectable by radio telescopes. Detecting it would allow astronomers to probe the Dark Ages, the period between the cosmic microwave background and the first galaxies. Efforts to detect this signal are underway, though they are extremely challenging. If successful, they would open a new window on the early universe, complementing the optical and infrared observations of the James Webb Space Telescope. The James Webb Space Telescope itself is approaching its own observational limit. As it looks at earlier and earlier galaxies, it is reaching toward the epoch when the first galaxies formed, the end of the Cosmic Dark Ages, when the first luminous structures lit up. The telescope can observe galaxies that have formed enough stars to be detectable, but it cannot observe the Dark Ages before the first galaxies, nor the first stars individually, which are too faint and too distant. The telescope is pushing toward the dawn of cosmic structure, but it has limits, set by the faintness and distance of the earliest objects. These limits remind us that there is much about the earliest universe that we may never directly observe. The first moments after the Big Bang, before the universe became transparent, are forever hidden from light-based observation. The Dark Ages before the first galaxies are extremely difficult to probe. Even the first galaxies and first stars are at the edge of what our most powerful telescopes can detect. Our knowledge of the earliest universe is, and will remain, incomplete, limited by the physics of what can be observed. And yet, within these limits, the James Webb Space Telescope has achieved a great deal. It has pushed our observations back to within a few 100 million years of the Big Bang, revealing the earliest galaxies and the conditions of the early universe in unprecedented detail. It has reached close to the fundamental limits of what light-based observation can achieve. The remaining gaps, the dark ages, the first moments, may eventually be probed by other means like radio observations of neutral hydrogen or, conceivably, by gravitational waves from the early universe. But the optical and infrared window has been pushed nearly to its limit by the James Webb Space Telescope, which has shown us the early universe more clearly than ever before, right up to the edge of what can be seen. To have reached that edge, within the span of a single human project, is a remarkable accomplishment in its own right. Beyond the limits of what we can observe lies a deeper question. What is the full extent of the universe, and how much of it can we ever know? The James Webb Space Telescope observes the most distant galaxies, near the edge of the observable universe. But the observable universe is not the whole universe. Understanding the relationship between the part we can see and the whole that may exist is a profound aspect of modern cosmology, touching on the ultimate limits of knowledge. The observable universe is the region from which light has had time to reach us since the Big Bang. Because the universe has a finite age, about 13.8 billion years, and light travels at a finite speed, there is a maximum distance from which light could have reached us. Objects beyond this distance are not observable, because their light has not had time to arrive. This defines the observable universe, a sphere, centered on us, with a radius set by how far light could have traveled, accounting for the expansion of the universe since the Big Bang. Due to the expansion of the universe, the observable universe is larger than one might naively expect. The most distant observable objects have been carried away by cosmic expansion as their light traveled toward us, so they are now much farther away than the distance light could travel in 13.8 billion years. The radius of the observable universe is about 46 billion light-years, even though the universe is only 13.8 billion years old because of this expansion. The observable universe is a vast region, containing billions of galaxies, but it is finite, bounded by the distance from which light has had time to reach us. The whole universe, however, is almost certainly larger than the observable universe, possibly much larger, possibly infinite. The observable universe is just the part we can see, limited by the finite age of the universe and the finite speed of light. Beyond the edge of the observable universe, there is presumably more universe, with more galaxies that we cannot see because their light has not reached us. How much more, we cannot say with certainty. The universe might be finite but much larger than the observable part, or it might be infinite. The observations do not settle the question, because we cannot see beyond the observable horizon. The James Webb Space Telescope, observing the most distant galaxies, is looking toward the edge of the observable universe, and, equivalently, toward the earliest times. The most distant galaxies are seen as they were in the early universe, because their light has taken nearly the whole age of the universe to reach us. There is a direct correspondence between distance and time. The farthest objects are the earliest objects. The edge of the observable universe in space corresponds to the beginning of cosmic history, in time. Looking outward is looking backward. This correspondence means that the telescope, in pushing toward the edge of the observable universe, is pushing toward the beginning of time. The earliest galaxies it observes are near both the spatial edge of the observable universe and the temporal beginning of cosmic structure. Beyond them, in space and time, lies the cosmic microwave background, the wall of the early opaque universe, and beyond that, the first moments after the Big Bang. The telescope is exploring the outer and earliest reaches of what can be observed, approaching the fundamental limits. What lies beyond the observable universe, the parts we can never see, is a matter of speculation and inference rather than direct observation. We can reason about it based on the assumption that the universe is roughly uniform on large scales, which suggests that the unobservable parts are probably similar to the observable parts. More galaxies, more cosmic structure, governed by the same physical laws. But we cannot observe these regions directly, and so our knowledge of them is necessarily indirect based on extrapolation from what we can see. This brings us to a humbling recognition. Our knowledge of the universe, vast as it has become, is bounded. We can observe only the observable universe, only back to the cosmic microwave background, only the structures bright enough and close enough to detect. Beyond these limits lies a universe we can reason about, but never directly see. The James Webb Space Telescope has expanded the boundaries of what we can observe, pushing back toward the beginning and outward toward the edge. But the boundaries remain. There is a universe beyond our sight, and there always will be. Our window on the cosmos, however much we enlarge it, opens onto only a part of the whole. The rest lies beyond the edge of the observable, in regions and times we can imagine but never witness. The story of what the James Webb Space Telescope revealed is not a finished story. It is a story still being written, in real time, by astronomers around the world working to understand the surprising observations. The puzzles raised by the telescope, the early massive galaxies, the early black holes, the little red dots, and their possible connection to the Hubble tension, are active areas of research, with new results appearing regularly. The cosmology of the early universe is being revised, refined, and rewritten as the work continues. This ongoing revision is not a sign of failure but of vitality. Science advances precisely through this kind of process. A surprising observation challenges existing theories. Researchers propose explanations, those explanations are tested against further observations, and gradually a new understanding emerges. The James Webb observations have set this process in motion for the early universe. The result over the coming years will be a better understanding of how the first galaxies formed, and possibly, if the deeper proposals prove correct, a revised understanding of cosmology itself. The current state of the field is one of productive uncertainty. The conservative explanation, that early star formation was more efficient than assumed, requiring revision of galaxy formation theory but not of fundamental cosmology, is favoured by most researchers and is consistent with the current evidence. But it is not the only possibility, and the more radical explanations involving new physics remain under investigation. The connection to the Hubble tension keeps open the possibility that something more fundamental is going on. The field has not reached consensus, and the question of whether cosmology was truly challenged remains genuinely open. What is clear is that the telescope has provided a wealth of new data about the early universe, data that was simply unavailable before. This data is the foundation on which the revised understanding will be built. Every new observation, every confirmed redshift, every measured mass, every detected element adds to the picture. The accumulation of data is gradually constraining the possibilities, ruling out some explanations and supporting others. Over time, the data will determine which explanations survive and which are discarded. The telescope continues to observe. It is still operating, still gathering data, still pushing the boundaries of what can be seen. New record-holding galaxies are still being found. New classes of objects, like the little red dots, are still being characterized. The early universe is still being explored, and there are surely more surprises to come. The story of what the James Webb Space Telescope revealed is far from over. In many ways, it is just beginning. The telescope is expected to operate for many years, and over that time it will continue to transform our understanding of the early universe. Other instruments will join the effort. The Atacama Large Millimeter Array, observing at longer wavelengths, can study the gas and dust in early galaxies, complementing the James Webb observations. Future telescopes, both in space and on the ground, will add further capabilities. Radio telescopes may eventually probe the cosmic dark ages. The picture of the early universe will be built up from many sources of data combined into an increasingly complete understanding. The James Webb Space Telescope is a central part of this effort, but it is not the only part. The revision of cosmology, if it occurs, will be a collective achievement, built from the work of many researchers using many instruments over many years. It will not be a single dramatic moment of breaking the old model and replacing it with a new one. It will be a gradual process of refinement and revision as the theories are adjusted to account for the growing body of observations. This is how science usually advances, not through sudden revolutions, but through the steady accumulation of knowledge and the gradual improvement of understanding. And so the cosmology of the early universe is still being written. The James Webb Space Telescope has opened a new chapter, revealing an early universe more active and more surprising than expected. The chapter is not yet complete. Researchers are still working out what the observations mean, still testing explanations, still gathering data. In time, a clearer picture will emerge. For now, we are in the midst of the process. watching as our understanding of the early universe is revised before our eyes. It is an exciting time to be paying attention to cosmology, a time when the textbooks are being rewritten and the story of the early universe is being told anew. To witness science in this unsettled state is a privilege of sorts. Most of what we learn about the universe arrives as settled fact, presented in textbooks long after the arguments have been resolved. But here, in the matter of the early galaxies, the argument is happening now, in real time, with the outcome genuinely uncertain. We are watching the process of discovery unfold, rather than reading about it after the fact. That is a rare and valuable thing to be able to observe. There is something profound in the simple fact that we can do this at all. That a species on a small planet orbiting an ordinary star in an ordinary galaxy can build an instrument capable of detecting light from the beginning of cosmic structure and can use that light to study the universe as it was more than 13 billion years ago. The James Webb Space Telescope is a remarkable achievement, not just technically, but in what it represents. The human capacity to reach out across unimaginable gulfs of space and time and learn about the origins of everything. The surprises the telescope revealed are, in a sense, a gift. It would have been less interesting if the telescope had simply confirmed what we already expected. Instead, it found something unexpected: galaxies that formed too fast, structures that assembled too early, objects that did not fit our theories. These surprises are invitations to learn, to revise our understanding, to discover something new about the universe. The fact that the universe surprised us is a sign that there is more to learn, that our knowledge is incomplete, that the cosmos still holds mysteries worth pursuing. This is the proper attitude toward the universe, humility combined with curiosity. We have learned a great deal about the cosmos, its age, its composition, its expansion, the formation of its structures. The standard model of cosmology is a triumph of human understanding, accounting for a vast range of observations with remarkable precision. But it is not complete. The James Webb observations, like the Hubble tension before them, remind us that there are things we do not yet understand, gaps in our knowledge, that the universe is pointing out to us. The appropriate response is not dismay but interest, the recognition that there is more to discover. The early galaxies that the telescope revealed are, in the end, our own distant ancestors, in a sense. The matter that makes up the Earth, the Sun, our bodies, was processed through generations of stars, beginning with the first stars in the first galaxies. The chemical enrichment that began in those early galaxies, the heavy elements forged in their stars, are the materials from which everything we know was eventually made. To study the early galaxies is to study our own origins, the first chapters of the long story that led, billions of years later, to us, to Psiogs. There is a connection across cosmic time between those first structures and our present existence. When you consider that the light from these galaxies has been travelling for more than 13 billion years, crossing nearly the entire history of the universe to reach a telescope built by human hands, there is a kind of wonder in it that is hard to put into words. The past is not gone. It is still arriving in the form of ancient light, carrying its information across the vast reaches of cosmic time. And we have learned to catch that light, to read its messages, to reconstruct from it the history of the universe. This is an extraordinary thing for a species to be able to do. The puzzles raised by the telescope, whether cosmology was broken or merely challenged, whether new physics is required or merely a better understanding of galaxy formation, will be resolved in time through continued research. But the resolution, whatever it turns out to be, will be less important than the process, the ongoing human effort to understand the universe, to push back the boundaries of knowledge, to learn what we do not yet know. The James Webb Space Telescope is a tool in that effort, a remarkable one, but the effort itself is larger than any single instrument. It is the long human project of trying to comprehend the cosmos in which we find ourselves. That project will never be finished. There will always be more to learn, more questions to ask, more mysteries to pursue. The universe is vast, and our knowledge of it, however much it grows, will always be incomplete. There will always be an edge to the observable, a limit to what we can see, a frontier beyond which lies the unknown. This is not a cause for despair, but for ongoing wonder. The universe will continue to surprise us, to challenge our theories, to invite us to learn, and we will continue to look, to study, to try to understand. So we end where we began, with a telescope, 1,000,000 miles from Earth, catching the faint light of the early universe and revealing a cosmos more surprising than we had imagined. The galaxies that should not exist, the structures that form too fast, the puzzles still unsolved. These are the gifts of a universe that is richer and stranger than our theories had supposed. We look back at the beginning across more than 13 billion years, and we find that we still have much to learn. There is a quiet humility in that recognition, and also a quiet joy. The universe is not finished revealing itself, and neither are we finished looking. That perhaps is enough for tonight.